Hello students, in our series of crash course, today we will study analytical chemistry. This is day 39 of crash course. This is disclaimer. So let's see what topics we are going to study today. So first we will study about qualitative inorganic analysis, in which we will study conformity test for group 1 anions. Then we will study conformity test for group 2 anions. After that we will study conformity test for group 3 anions. And finally we will study cations or basic radicals. So let's begin our lecture with qualitative inorganic analysis. So what is qualitative inorganic analysis? Qualitative analysis deals with the detection and identification of various constituents present in the inorganic salt or a mixture of salt. So it means identifying which ions or constituents are present in any inorganic salt or mixture of salt. So there are two kinds of analysis. First qualitative, second quantitative. Quantitative deals with the quantity, which means how much, how many anions, what is the quantity of anions present. But in qualitative analysis, we just deal with the identification of ions, which ions are present in any or inorganic salt or mixture of salt. So inorganic salts are formed from the neutralization reaction of acid and base. So inorganic salts are the product of neutralization reaction of an acid and a base. Acid produces H plus in solution and base produces hydroxide ions in solution. So inorganic salt have two parts. They contain an anion and a cation. So when we identify both ions, we can easily tell the name of the salt. So now we'll study about anions or acid radicals. Sorry for the interruption. So next we will study about anions or acid radicals. So anions are also called acid radicals because they are derived from acids. These are divided into three groups based on their reaction with dilute and concentrated sulfuric acid. Some give characteristic reaction with dilute H2SO4, some only react with concentrated H2SO4, while some anions do not react with either dilute H2SO4 or concentrated H2SO4. So based on this, these acid radicals are divided into three groups: group 1, group 2 and group 3. So group 1 anions react with dilute sulfuric acid. Group 2 anions only react with concentrated sulfuric acid. These anions, that is group 2 anions, do not react with dilute sulfuric acid. Group 3 anions do not react with either dilute or concentrated H2SO4. So, anions or acid radicals are divided into three groups depending upon the reactions with dilute and concentrated H2SO4 or sulfuric acid. Group 1 anions react with dilute H2SO4. Group 2 anions only react with concentrated sulfuric acid. And group 3 anions do not react with either dilute or concentrated sulfuric acid. I hope this is clear to you. So now let's see what happens when group 1 anions react with dilute sulfuric acid. So here we have a table comprising group 1 anions and gases evolved when these group 1 anions react with dilute sulfuric acid. So group 1 anions contain carbonate, sulfide and nitrite. So when carbonate, its molecular formula is CO3 2 minus. So when this carbonate anion react with dilute H2SO4, what happens? We observe brisk effervescence of CO2. Brisk effervescence means rapid vigorous bubbling. So when carbonate, this react with dilute H2SO4, we observe rapid bubbling of CO2 gas. When we react sulfide, its molecular formula is SO3 2 minus. So when we react sulfide SO3 2 minus with dilute H2SO4, we observe colorless gas with odor of burning sulfur. So a colorless gas is formed which smells like burning sulfur, and this gas is sulfur dioxide SO2. So when sulfide reacts with dilute H2SO4, SO2 is evolved, sulfur dioxide. And next group 1 anion is sulfide. Its formula is S2 minus. When sulfide react with dilute H2SO4, colorless gas having smell of rotten eggs is evolved, and this gas is H2S, hydrogen sulfide. So this gas has a smell of rotten eggs. So when sulfide react with dilute H2SO4, H2S gas is released. And next we have nitrite ion. Its formula is NO2 minus. So when this anion react with dilute H2SO4, we observe brown fumes with pungent odor. And these brown fumes of which gas? These are of NO2 gas. So when nitrite NO2 minus react with dilute H2SO4, NO2 gas is evolved. So we saw which are group 1 anions. They are carbonate, sulfide, and nitrite. So carbonate evolves CO2, sulfide gives SO2, sulfide S2 minus, it gives H2S gas, and finally nitrite, it gives NO2 gas. Now we'll talk about group 2 anions. Group 2 anions react with concentrated H2SO4. Group 1 was reacting with dilute H2SO4, but group 2 anions, they react with concentrated H2SO4. Let's see what happens when they react with concentrated sulfuric acid. So here we have a table comprising group 2 anions and gases evolved with concentrated H2SO4. So in group 2 anions we have chloride Cl minus, bromide Br minus, iodide I minus, and nitrate NO3 minus. So when group 2 anions react with concentrated H2SO4, which gas is evolved? We will see one by one. So from chloride anion Cl minus, a colorless gas is evolved when it reacts with concentrated H2SO4, and this gas has a pungent smell. So what is this gas? This gas is HCl, hydrogen chloride. So when bromide react with concentrated H2SO4, we observe brown fumes. Brown fumes are evolved. These fumes are of which gas? Bromine gas, Br2. When iodide I minus react with concentrated H2SO4, violet fumes are formed, and these fumes are of which gas? Iodine gas, I2 gas. And finally, from nitrate, What is the chemical formula of nitrate? It is NO3 minus. So when nitrate react with concentrated H2SO4, we observe which gas? Nitrogen dioxide gas, NO2 gas. It is pungent and light brown. So when chloride anion react with concentrated H2SO4, which gas is evolved? HCl gas. When bromide is reacting with concentrated H2SO4, we observe brown fumes of Br2 gas. When iodide react with H2SO4, iodine gas is formed. And when nitrate react with concentrated H2SO4, NO2 gas is evolved. So these are the group 2 anions and these are the gases evolved with concentrated H2SO4. So moving on, group 3 anions. Group 3 anions do not react with either dilute or concentrated sulfuric acid. Group 1 anions react with only dilute H2SO4. Group 2 anions react with concentrated H2SO4. But group 3 anions, they do not react with either dilute H2SO4 or concentrated H2SO4. They are not affected by both dilute as well as conc H2SO4. Now we'll see which ions are present in group 3 anions. So in group 3 anions, we have sulfate and phosphate ions. So sulfate and phosphate ions are present in group 3 anions. These sulfate ions and phosphate ions, they are not affected by both dilute as well as conc H2SO4. I hope this is clear to you. This is clear, then send me a thumbs up in the chat box. Now we will look at the confirmatory test for group 1 anions. So till now we discussed the preliminary test for group 1 anions, which means the initial test. We perform for group 1 anion, group 2 anions and group 3 anions by reacting with the respective H2SO4. We reacted group 1 anions with dilute H2SO4, group 2 anions with conc H2SO4 and group 3 anions do not react with either dilute H2SO4 or conc H2SO4. Now we'll look at the confirmatory test for group 1 anions. So following anions decomposes on reaction with dilute H2SO4 to give gases. So if we have group 1 anions, then which test can we perform to confirm the presence of these ions are the confirmatory test. We know group 1 anions decompose upon heating with dilute H2SO4 to give gaseous product. And from these gases, we can indicate the nature of the acid radical present in the salt, which means we can identify the anion present in the salt. Salt have two parts, cation and anion. And using these confirmatory tests we are going to study, we can identify the nature of the anion present in the salt. So let's see, first comes the carbonate anion, CO3 2 minus. So when we react carbonate anion with dilute H2SO4, CO2 gas is obtained from the carbonate. To identify this gas, which gas is evolved? To identify this gas, what we do? We pass this gas through lime water. Now what is lime water? Lime water is a clear colorless solution of calcium hydroxide in water. CaOH whole twice, calcium hydroxide in water. So colorless solution of calcium hydroxide in water is known as lime water. When CO2, carbon dioxide, passes through lime water, CaCO3 is formed, calcium carbonate is formed. So when CO2 is passed through lime water, that is aqueous solution of calcium hydroxide, CaCO3 is formed, calcium carbonate. And due to the formation of calcium carbonate, lime water turns milky. Why lime water turns milky? Because calcium carbonate has formed, and due to the formation of calcium carbonate, its color and texture becomes milky. So this gas is recognized by passing it through lime water, which turns milky due to the formation of CaCO3. And if we use an excess of CO2, if we pass excess of carbon dioxide gas through lime water, what will happen? Calcium bicarbonate will be formed. initially calcium carbonate was formed. If we pass excess of CO2, then calcium bicarbonate will be formed. This calcium bicarbonate is soluble and completely colorless. Therefore, first the lime water turns milky, and when more CO2 is passed, it becomes colorless again because calcium bicarbonate has formed and it is soluble in water. CaCO3 calcium carbonate, it is insoluble in water, and due to the formation of CaCO3, lime water turns milky. But when excess of CO2 is passed, then calcium bicarbonate starts forming, and this calcium bicarbonate is soluble in water. Therefore, the solution becomes colorless again. So this confirms the presence of CO2 gas. So when carbonate CO3 minus react with dilute H2SO4, CO2 gas is indeed formed. It is recognized by passing it through lime water. So this is the reaction of calcium carbon dioxide with calcium hydroxide, that is lime water. The formation of calcium carbonate is taking place, due to which solution turns milky. So this is the reaction involved when carbon dioxide react with calcium hydroxide aqueous solution. CaOH whole is reacting with CO2, forming CaCO3. It is a white precipitate which turns solution milky. And when there is excess CO2, the calcium bicarbonate will be formed. So here is the equation, chemical equation given: CaCO3 plus H2O liquid plus CO2 gaseous, which is excess. Then they all react with each other to form calcium bicarbonate. HCO3 minus is bicarbonate. So Ca HCO3 whole twice is calcium bicarbonate. It is soluble in water. So solution will become colorless again. So these are the chemical reactions involved when carbon dioxide gas is passed through lime water. So now moving on. Next we have sulfide ion, SO3 2 minus. When sulfide react with dilute sulfuric acid, a pungent smelling gas is released, which is SO2. So when sulfide react with dilute H2SO4, which gas is released? SO2, and it is pungent smelling gas. This SO2 gas turns acidified K2Cr2O7, acidified potassium dichromate paper, green. This gas turns acidified K2Cr2O7 paper green. Why? Because potassium dichromate is orange in color and it contains chromium in +6 oxidation state. So what is the oxidation state of chromium in K2Cr2O7? It is +6. So when SO2 gas is passed over acidified K2Cr2O7 paper, it reduces Cr6 plus to Cr3 plus, which means chromium ion is undergoing reduction, Cr6 plus to Cr3 plus. Due to this, due to the reduction of chromium atom, the color of paper changes from orange to green. So SO2 reduces this K2Cr2O7. It reduces Cr6 plus to Cr3 plus. So here SO2 is acting as reducing agent because it is reducing K2Cr2O7, and because it reducing potassium dichromate, the paper turns green. So this is the chemical equation involved in the reaction. K2Cr2O7 plus H2SO4 plus 3SO2, they all react with each other to form K2SO4 plus Cr2SO4 whole thrice plus H2O. So when K2Cr2O7, acidified K2Cr2O7 react with SO2 gas, it forms chromium sulfate Cr2SO4 whole thrice, which is green in color. So oxidation state of chromium has reduced from +6 to +3, and due to this solution has given a green color. So just like SO2, we have another gas H2S. It also turns potassium dichromate paper green. So therefore, before testing for sulfide ion, that is SO3 2 minus, we should test for S2 minus, that is sulfide ion. And if it is present in our solution, then it should be removed. Since H2S gas also turns potassium dichromate paper green, therefore, before testing for sulfide ion SO3 2 minus, we must test for presence of sulfide ion S2 minus. And if it is present in our solution, then this ion should be removed, because it is possible that our paper, the acidified K2Cr27 paper, is turning green due to S2 minus ion, not due to SO2. So this sulfide ion can interfere in the confirmatory test for sulfide ion. Therefore, we must remove sulfide ion S2 minus before testing for sulfide ion SO3 2 minus. So for this reason, we need to first test for presence of S2 minus before SO3 2 minus. If S2 minus is present, then remove it, and if not, then test for SO2. So next ion is sulfide S2 minus. In this, the gas released is H2S gas. Its test is done with lead acetate paper, which turns black on reaction with H2S because black like sulfide is formed. So this H2S gas is tested with lead acetate paper, which turns black due to the formation of black lead sulfide. So this is the chemical reaction involved. So when lead acetate, which is CH3 COO whole twice Pb, it react with H2S, it gives a black colored PBS, lead sulfide. It is a precipitate, and along with acetic acid, CH3COOH is also formed. So H2S gas is tested with lead acetate paper. Lead acetate paper turns black due to the formation of black lead sulfide. And when H2S is reacted with sodium nitroprusside, what is the formula of sodium nitroprusside? It is NO2 FeCN whole 5 NO. So when H2S is reacted with sodium nitroprusside, it gives violet color. Why we see violet color? It happens because of the formation of sodium thionitroprusside. What is the formula of sodium thionitroprusside? It is Na4 FeCN5NOS. So because of the formation of this complex sodium thionitroprusside, H2S gives a violet color with sodium nitroprusside, Na2FeCN5NO. So these are the confirmatory tests for H2S gas, or we can say sulfide ion H2S. So for sulfide ion SO3 2 minus, the confirmatory test is reaction of SO2 with acidified K2Cr27 paper, and if the paper turns green, this confirms the presence of SO2 gas, which further confirms the presence of sulfide ion SO3 2 minus. And to test the presence of sulfide ion S2 minus, the gas evolved H2S can be reacted whether with lead acetate paper, which turns black due to the formation of black lead sulfide, or this can be reacted with sodium nitroprusside, which then H2S will give violet color because of the formation of sodium thionitroprusside complex. So next ion is nitrite ion NO2 minus. So in this, the gas released oxidizes I minus to I2, which gives a blue color with starch. So when nitrite NO2 minus is reacted with dilute H2SO4, the evolved gas What does it does? The evolved gas oxidizes I minus, that is iodide ion, to I2, and this I2 gives blue color with starch, which it means that when nitrite reacts with dilute sulfuric acid, the gas released is NO2, nitrogen dioxide, and it converts I minus to I2, and this I2 gives blue color with starch. So let's see the chemical reaction involved in this test. So this is the chemical equation. 2Ki plus 2NO2 gaseous, they react to form 2KNO2 plus I2 aqueous. So this NO2 gas, which is evolved when nitrite ion react with dilute H2SO4, when this NO2 gas is reacted with iodide minus, here this is potassium iodide, then this NO2 gas acts as oxidizing agent. It oxidizes I minus to I2 gas, and this I2 gas is present in aqueous form. And if we react with this I2, this iodine aqueous, with starch, a starch iodide complex is formed, and this complex is blue in color. From this, we came to know that nitrite ion was present in the sample. So these all are confirmatory tests for group 1 anions. Now we will study the confirmatory test for group 2 anions. That is, we will see how the test for group 2 anion is performed. When these anions react with concentrated H2SO4, gases are released. So we know that we react group 2 anions with conc H2SO4. They do not react with dilute H2SO4. So the group 2 anions decomposes on reaction with concentrated H2SO4 to release gaseous product. Therefore, we will test these anions based on which gas is being released. So the first anion is chloride anion, Cl minus. So chloride ions release hydrogen chloride, that is HCl, gas on reaction with conc H2SO4. So when chloride anions react with conc H2SO4, which gas is released? HCl gas is released. And to identify this gas, when we dip a rod in ammonium hydroxide and bring it to the mouth of the test tube, dense white fumes are formed which are of NH4Cl. So this indicates that chloride is present in our compound. The white fumes that are released are of NH4Cl. So how can we confirm whether this gas is present or not? It is identified by bringing a rod dipped in ammonium hydroxide. It is a weak base. So we will bring a rod dipped in ammonium hydroxide near the mouth of the test tube. And when dense white fumes NH4Cl are produced, this confirms the presence of HCl gas. Then we can see the chloride ions were present. The next test for chloride is chromyl chloride test. This is a confirmatory test for chloride. When we heat a chloride salt, which means a salt having anion as chloride. So when we heat a chloride salt with solid K2Cr27, that is potassium dichromate, and concentrated H2SO4, it produces orange yellow vapor of chromyl chloride, CrO2Cl2. Therefore, when solid K2Cr27 react with conc H2SO4, CrO2Cl2, which is chromyl chloride, are formed. This compound is very important. This test is very important. So, when this K2Cr2 react with H2SO4, what is formed? Chromyl chloride, CrO2Cl2. This gas is formed. When these vapors are passed through, when these orange yellow vapors of chromyl chloride is passed through NOH and then treated with lead acetate, then a yellow colored precipitate of lead chromate is formed. And this is our test for chloride, that is chromyl chloride test. So, on heating with K2Cr2O7 and conc H2SO4, chloride gives orange yellow vapor of chromyl chloride. And when these chromyl chloride vapors are passed over NaOH and then on treating with lead acetate, It forms yellow precipitate of lead chromate. This confirms the presence of chloride ions. So now let's look at the reactions involved in the chromyl chloride test. So on reaction of chloride ion, here the salt is NaCl, sodium chloride. We can see it has chloride ion as anion. So on reaction of chloride ion with potassium dichromate, that is K2Cr2O7 and Conc H2SO4, what is formed? CrO2Cl2, that is chromyl chloride, is formed. That appears as orange yellow fumes. So when chloride ion react with potassium dichromate and Conc H2SO4, chromyl chloride is formed. We will observe the orange yellow fumes of chromyl chloride along with K2SO4, 3H2O and Na2SO4 are also formed as byproduct. So then on reaction of this chromyl chloride with sodium hydroxide. So when we react this chromyl chloride with sodium hydroxide NaOH, yellow solution of sodium chromate, that is Na2CrO4, is produced. So when this chromyl chloride react with sodium hydroxide NaOH, Na2CrO4, that is sodium chromate, is produced, which is yellow in color. So we'll observe the yellow solution because of the formation of sodium chromate Na2CrO4 along with NaCl, and water is also formed as byproducts. So to the above solution, lead acetate is added. So we will add the lead acetate to the above solution. This is a reaction of sodium chromate with lead acetate. So the chromium acetate that is formed, that is sodium chromate that is formed, it react with lead acetate and they react to form lead chromate. Yellow precipitate of lead chromate is formed, PbCrO4. So the formation of lead chromate confirm the presence of chloride ion. So these are the reactions involved in the chromyl chloride test. Chromyl chloride test is not given by chlorides of HeSN, Ag, Pp and Sp because these do not liberate free chloride ions easily. So if we have the chloride salt of He, mercury, tin, silver, lead or antimony, if we have the chloride salt of these metals or these, then they do not give chromyl chloride test because they do not liberate free chloride ion easily. Next test for chloride is when chlorides are treated with HNO3, nitric acid and AgNO3, that is silver nitrate, a white precipitate of AgCl is formed, that is silver chloride. This AgCl precipitate is soluble in NH4OH, that is ammonium hydroxide, confirming it as AgCl. So, chloride on treating with the mixture of silver nitrate and HNO3, that is nitric acid, it forms a white precipitate of AgCl, silver chloride, and this silver chloride is soluble in NH4OH. So this confirms the presence of chloride ion. Next we have bromide anion, Br minus. So bromide ions release bromine gas on reaction with concentrated sulfuric acid, which has brown fumes. So the evolved gas, when Br2 react with conc H2SO4, evolved gas is Br2 and produces raw brown fumes. This indicates the presence of bromide ions, Br minus ions. And when bromides are treated with HNO3 and AgNO3 solution, a light yellow colored precipitate of AgBr is formed, and this AgBr is partially soluble in excess of NH4OH. So this confirms the presence of bromide ions because when we treat bromides with the mixture of HeNO3 and HNO3, a yellow precipitate, pale yellow precipitate of HEPR, that is silver bromide is formed, and this silver bromide is partially soluble in excess of NH4C. NH4OH, as we have already discussed, for in the case of chloride ion, what is formed? HeCl is formed, and this HeCl is soluble in NH4OH. But this HEPR, this is yellow precipitate, and this is not soluble. This is partially soluble in excess of NH4OH. So next, for the conformation of bromide ion is layer test. So what is this test? In this, bromides are mixed with chlorine water and chloroform. The chloroform layer turns yellow. Therefore, this is called layer test because the chloroform layer is turning yellow. This layer is confirming the presence of bromide ion. So when we shake bromide with chlorine water and chloroform, the chloroform layer turns yellow, or we can say brownish yellow. This confirms the presence of bromide ion. So what is the role of chlorine water here? So the chlorine water Cl2, it oxidizes bromide ion to Br2, and this Br2 gives yellow color in chloroform layer, that is CHCl3. So this confirms the presence of bromide ion in our sample. So this is the chemical reaction taking place. So 2Br, that minus, that is bromide ion, plus Cl2. So Cl2 acts as oxidizing agent, it oxidizes Br minus to Br2, that is bromide ion to bromine molecule Br2. And due to this, the chloroform layer turns yellow. Formation of Br2, the chloroform layer turns yellow because this is soluble in CHCl3. The fourth anion is iodide anion, that is I minus. So iodide ions react with concentrated sulfuric acid to give deep violet vapors of iodine gas. Thus, gas evolved in this case is I2. The evolved iodine gas can be identified by treating it with starch solution. The I2 gas, when treated with starch solution, it turns blue. So when iodide ion react with conc H2SO4, the evolved gas is I2, and this I2 gas has deep violet vapors. The obtained I2 gas is recognized by treating it with starch solution because I2 gas forms complex with starch iodide complex, which is blue in color. So this is the word equation for the reaction involved. So when we add I2 to starch, we obtain a starch iodine complex, which is blue in color. And if we perform a layer test for iodine, the CHCl3, that is chloroform layer, will appear violet in color. So on performing the layer test for bromide ion, what does we observe? We observe the yellowish brownish layer in the CHCl3. But if we perform a layer test for iodide ion, the CHCl3 layer will turn violet. Now let's look at the confirmatory test for nitrate ion. When nitrate salts are treated with concentrated sulfuric acid, colorless nitric acid is produced. This nitric acid decomposes on heating to produce brown fumes of nitrogen dioxide gas. So on reaction with conc H2SO4, first form colorless HNO3, which decomposes to form brown fumes of nitrogen dioxide. So eventually, which gas is evolved? Nitrogen dioxide, NO2. And we observe the brown fumes of NO2. So NO2 has characteristic color, brown. Now, the confirmatory test for nitrate ion is ring test. What is this ring test? In this test, the solution of nitrate salt is first mixed with freshly prepared iron sulfate, that is FeSO4. Then concentrated sulfuric acid is carefully added because it is very corrosive. So we have to handle conc H2SO4 very carefully. So It is added very carefully along the side of the test tube so that it forms a separate layer below the solution. If nitrate ions are present, a chemical reaction produces nitric oxide NO. This nitric oxide NO then combined with Fe2 plus ions to form a brown colored complex. This brown ring appears exactly at the junction of these two layers. The appearance of this dark brown ring confirms the nitrate ions are present in the sample. So this is very important test. This is the ring test is very important test for the nitrate. The water extract of nitrate salt is treated with freshly prepared iron sulfate, ferrous sulfate solution, and then Kong ester is added. And the formation of dark brown ring between the two layers confirm the presence of nitrate radical, that is nitrate anion. So what are the reactions that are involved in the ring test? So the nitrate salt, here we have the sodium nitrate NaNO3. When this reacts with Kong H2SO4, this forms HNO3. This liberates nitric acid. So first form the nitric acid HNO3 along with NaHSO4 is also formed as byproduct. Then FeSO4 solution acts as a reducing agent and it reduces nitric acid to nitric oxide gas. So FeSO4 ferrous sulfate acts as reducing agent and it reduces nitric acid HNO3 to nitric oxide NO. As we can see in the reactant side we have HNO3 nitric acid and in the product side we have nitric oxide. So when FeSO4 react with HNO3 it forms nitric oxide NO gas along with Fe2SO4 whole thrice and water is also formed as byproduct. The freshly produced NO2 gas react with Fe2 plus ion present at the boundary. This leads to the formation of brown colored complex and the dark brown ring confirms the presence of nitrate ion. So NO combines with the Fe2 plus ions. Fe H2O whole 6 SO4. So this complex contains Fe2 plus ion. So Fe2 plus ion react with NO gas, nitric oxide gas and it forms dark brown ring. What is the formula of this complex? FeH2O5NO2 plus SO4 2 minus. So this is the dark brown ring. We also call it brown ring complex. This the formation of dark brown ring confirm the presence of nitrate ion. The oxidation state of Fe in brown ring is +1. This is very important. The oxidation state of Fe. Now we'll study the conformity test for group 3 anions. Till now we discussed the conformity test for group 1 anions and group 2 anions. Now we'll discuss the conformity test for group 3 anions. So we know the group 3 anions do not react with either sulfuric acid, Kong sulfuric acid or dilute sulfuric acid. So we will study the conformity test for group 3 anions. We know the sulfate ion belong to group 3 anion. What is the formula of sulfate ion? It is SO4 2 minus. So SO4 2 minus is our group 3 anion. For the conformation of sulfate, we perform the BaCl2 test. The white precipitate of BaSO4, barium sulfate, is insoluble in concentrated HNO3, which means that white precipitate of BaSO4 do not dissolve in HNO3. So this is the conformity test for sulfate, BaCl2 test. The white precipitate which forms is insoluble in Kong HNO3. Now we will study about cations or basic radicals. Till now we study about anions or acid radicals. Now we'll study about the cationic part, the basic radical of the salt. So first we will study some dry test method that can be used to identify cations. So what is dry test? Dry test refers to the method of qualitative analysis performed on a solid sample without dissolving it in a solvent. So there is no use of solvent in these tests. Therefore, this is known as dry test method. So the first test is the flame test. So what is the first dry test? It is flame test. We use this test to identify cations because different cations give different colors. So flame test is used to identify the cations by developing different colors. So on the basis of the different colors, we can identify the cations. So these are as follows. So here a table has been provided in which on one side the names of the radical are given and on the other side their color in the flame test is given. So sodium Na plus sodium cation gives golden yellow color. Lithium ion, that is Li plus, it gives crimson red color. Potassium ion K plus, it gives violet color. Copper Cu2 plus, it produces bluish green color. Calcium Ca2 plus ion, it produces brick red or dull red color. Strontium Sr2 plus, it gives crimson red color. And barium Ba2 plus, it gives apple green color. So all these colors are given by these cations. We should determine from the flame test to identify which cation gives which color. So if we know the color, then we can identify the radical. So this is important to remember the color which is obtained when the anions are undergoing, cations are undergoing flame test. Second dry test is borax bead test. This test is used to identify colored metal cations by observing the color produced when the metal salt is heated with borax in different types of flames. So, for example, we have some basic radicals such as nickel Ni, gold Au, aurum, chromium Cr, iron Fe, copper Cu. Now, in borax bead test, if we take an oxidizing flame which contain excess oxygen and the oxidizing flame is non-luminous. Non-luminous means it gives clean flame, that is blue flame. Combustion is complete here. So if we take an oxidizing flame which is non-luminous, then what color does it give with its ions? Nickel gives light brown, gold gives rose violet, chromium gives green color, iron produces yellow color, while copper gives light blue or green color. Now if we take reducing flame which is luminous, what is reducing flame? Reducing flame contains acetylene more than oxygen and it is luminous, which means the color is yellow. Incomplete combustion is taking place here. So in reducing flame, nickel gives black color, gold gives violet color, chromium gives green color, iron gives bottle green color, and copper gives colorless or red color flame. So that is how we can identify the cation using borax speed test based on the color in different flames. So borax speed test is done only for colored substances. This is very important. So when we perform borax speed test, then we do it for those substances which are colored. So here nickel, gold, chromium, iron, copper, these are all colored substances. Now moving on to wet test. Till now we discussed the two type of dry test. Now we'll discuss the wet test. Wet tests are chemical tests done in solution to identify cations. Cations are divided into groups based on the reagent that precipitates them. So, basic radicals, that is cations, have been divided into 6 groups on the basis of solubility product and the reagent used. So, on the basis of solubility product and the reagent, the basic radicals can be classified into how many groups? Into 6 groups. So, here we have a table. First comes group 0. Group 0 includes which cation? NH4 plus, that is ammonium cation. And we will use NaOH for group 0. So the group reagent for group 0 is NaOH, that is sodium hydroxide. Group 1 includes Pb2 plus, Ag plus and He2 2 plus. Group reagent for group 1 is dilute HCl. Group 2 includes Pb2 plus, Cu2 plus, Bi3 plus, Cd2 plus and Sn2 plus. Group reagent for group 2 is H2S in the presence of dilute HCl. Group 3 contain 3 cations Fe3 plus, Al3 plus and Cr3 plus. What is the group reagent for group 3? It is NH4Cl plus NH4OH. Group 4 contain Ni2 plus, Zn2 plus, Mn2 plus and CO2 plus. Group reagent for this group is H2S in the presence of NH4OH. For group 5, it contains Ba2 plus, Ca2 plus and Sr2 plus ions. Group reagent for this group is NH4 whole twice CO3, that is ammonium carbonate, in the presence of NH4Cl and NH4OH. And for group 6, we have magnesium ion Mg2 plus. And group reagent for this group 6 is Na2HPO4. So these are the radicals of different groups from group 0 to 6 and their group reagents are also given here. So we have to memorize this group reagent for different groups. So now we'll study some tests, some confirmative test for 0 group, that is NH4 plus. 0 group contain which cation? NH4 plus. So let's look at how to identify NH4 plus. When the ammonium ion is heated with NaOH, that is sodium hydroxide, ammonia gas is evolved, that is NH3 gas is evolved, which can be identified when glass rod dipped in HCl is brought near the mouth of the test tube as the white fumes of NH4Cl are produced. So NH3 react with HCl gas to produce white fumes of NH4Cl ammonium chloride. So ammonium ion first on heating with NaOH produces which gas? Ammonia gas, NH3 gas. And this gas is recognized by taking a glass rod dipped in HCl above the mouth of test tube. It's because it produces white fumes of NH4Cl. So if you observe white fumes, then ammonium ion is present because the gas is NH3. And the reaction of ammonia gas and Nessler reagent produces a yellowish brown color precipitate. So this ammonia gas, NH3 gas, gives yellowish brown precipitate with Nessler reagent. So here we have the chemical reaction. So K2HEI4 is called Nessler reagent. So what is the formula of Nessler reagent? It is K2HEI4. We reacted it with ammonia plus NaOH. So K2HEI4 plus NH3 plus 3 molecules of NaOH. They all react to form the iodide of Milon space. Iodide of which base? Milon space. This is yellowish brown precipitate. So this is the structure of this complex. Along with it, we get Ki, Nai, NH2. So this the formation of yellowish brown precipitate. This confirms the presence of ammonium ion because ammonium ion produces NH3 gas on heating with NaOH. And we can confirm this NH3 gas using this two tests. First, we can react this with HCl or we can react this with Nessler reagent. So that's all about the theory part. Now we'll discuss some questions. So give me a moment. So let's start with question number 1. A substance when treated with dilute sulfuric acid liberates a colorless gas, and this gas produces turbidity with barita water. What is barita water? It is aqueous solution of barium hydroxide, BaOH whole twice. So this gas produces turbidity with barita water and turns acidified dichromate solution green. So based on this observation, we are going to identify which ion is present in the substance. 4 options are given to us. A. Carbonate anion CO32 minus. B. Sulfide anion S2 minus. C. SO32 minus. Or D. NO2 minus. So after doing this question, we will have understanding of the chemical behavior of certain anions in acidic condition and the identification of gases based on their reaction with a specific reagent. So does anybody know the correct answer of this question? So type the option in the comment box. Let's move toward the solution now. So correct answer of this question is option C, SO3 2 minus. So sulfide ion SO32 minus react with dilute sulfuric acid to produce sulfur dioxide SO2. So SO32 minus react with dilute H2SO4. We know this is a group 1 anion. So it react with dilute H2SO4 to produce SO2 gas, sulfur dioxide, and this gas forms a turbid solution with barium hydroxide, and this gas also reduces acidified dichromate to clean chromium 3 ions, showing its reducing nature. So SO2 is a reducing agent. It reduces acidified dichromate, that is potassium dichromate solution, green, due to the reduction to Cr3 plus ion. The oxidation state of chromium decreases from +6 to +3. And this gas gives turbidity with barita water, which is aqueous solution of barium hydroxide, BaOH whole twice. The reaction here shows sulfide ions reacting with dilute sulfuric acid to produce sulfur dioxide gas. Sulfide SO32 minus react with H2SO4 to release SO2, which is a colorless gas. Now this reaction shows the reduction of dichromate Cr2O2O72 minus, that is dichromate ion, to chromium 3 sulfate Cr2SO4 whole thrice, turning green in acidic condition with sulfur dioxide SO2 acting as a reducing agent. So the reaction involves electron transfer where Cr6 plus. So this dichromate contain Cr chromium in which oxidation state in +6. So this chromium 6 plus is reduced to chromium 3 plus because of SO2. SO2 acts as ion reducing agent and reduces Cr6 plus ion to Cr3 plus ion. When CO32 minus react with dilute H2SO4, it gives CO2 gas. If we talk about other options, so carbonate ion, it reacts with dilute H2SO4 to produce CO2 gas, carbon dioxide gas. S2 minus sulfide, it forms H2S gas when react with dilute H2SO4, and NO2 minus produces NO2 gas. These reactions show different anions react with acid to form various gases and compounds. So here we have next question. The brown ring test for nitrite NO2 minus and nitrate NO3 minus is based on the formation of a complex ion. This question asks us to identify the correct formula of this complex ion from the given options. So when you perform the brown ring test, a complex is formed. We have to identify its formula. Options are A, FeH2O whole 6 2 plus, B, FeNO whole 5 2 minus. Option C, FeH2O whole 5 NO2 plus, or option D, FeH2O NO whole 5 2 plus. If anybody knows the correct answer of this question, then write in the comment box. So moving towards the solution. So the correct answer of this question is option C. So what is the formula of the complex ion? It is FeH2O whole 5 NO2 plus. So let's discuss the solution. So the Brown ring test for nitrate and nitrite is due to the formation of FeH2O whole 5 NO2 plus complex ion. So Brown ring test for NO2 minus, that is nitrite, and nitrate NO3 minus, it is a qualitative method used to detect the presence of nitrate ions NO3 minus in a solution. The test involved the reaction of nitrate ions with iron 2 sulfate FeSO4 in the presence of concentrated sulfuric acid H2SO4. When nitrate ions react with iron 2 sulfate and concentrated sulfuric acid, they form FeH2O5NO2 plus complex. This complex appears as brown ring at the interface. This complex forms the nitrate reaction with Fe2 plus and H plus. So this reaction shows nitrate ion NO3 minus acting as an oxidizing agent. It oxidizes ferrous ion Fe2 plus to ferric ion. So oxidation state of Fe is changing from 2 plus to 3 plus. Nitrate ion NO3 minus oxidizes ferrous to ferric ion in acidic condition. Nitric acid HNO3 is involved as it provides H plus and NO3 minus. And in this reaction, water is formed as a byproduct. And this reaction shows FeH2O whole 6 2 plus when react with NO to form brown complex FeH2O whole 5 NO2 plus and water. Here NO coordinates to the iron center, replacing one water molecule, resulting in a color change with a new complex electronic structure. So this, the formation of brown complex, gives the brown ring test, which confirms the presence of nitrate and nitrites in the sample. So this is the formula of the complex ion. So the correct option is option C. Let's move on to the question number 3. The question asks, acidic solution of what type of salt produces a deep blue color when reacted with starch iodide solution? And which of the given options could be the correct answer? Options are A, chloride, B, nitrite, C, acetate, or D, bromide. So let's move toward the solution. The correct answer is option B, nitrite. Starch iodide solution contains iodide ion, and iodide ions are oxidized by nitrate ions, that is NO2 minus, to form iodine I2. Iodine react with starch to produce a blue color. So this reaction shows the oxidizing property of NO2 minus. So here is the reaction involved. The reaction shows nitrous acid HNO2 reacting with potassium iodide Ki and acetic acid CS3COOH to produce iodine I2, which turns blue with starch because it forms a starch iodide complex which is blue in color. So iodine is formed via redox reaction where HNO2 acts as an oxidizing agent and Ki provides iodide ions. So the acidic solution of salt produces a deep blue color with starch iodide solution, and the salt may be nitrite. So moving on to next question. When borax is heated on a platinum wire, it forms a glass-like bead. So this question is asking about the composition of this bead. So what is this composition? When borax when heated on platinum wire, it forms a glass-like bead, and this glass-like bead is made up of. You have to identify the correct option. Our options are A. Sodium tetraborate, B. Sodium metaborate, C. Sodium metaborate and boric anhydride, or option D. Boric anhydride and sodium tetraborate. Let's move on to the solution. Correct answer is option C. Sodium metaborate and boric anhydride. When borax is strongly heated, it first loses its water of crystallization to form anhydrous borax. So when borax is strongly heated, it loses the water molecule which is attached to it. That is water of crystallization. It loses it. Then on further heating, it leads to the production of sodium metaborate, NaBO2, and boric anhydride, B2O3, forming a glassy bead. This process involves dehydration and decomposition, resulting in a transparent glass-like substance. The given equation shows borax Na2B4O7.10H2O. So this is the formula of borax, Na2B4O7.10H2O. So when it is strongly heated, it dissociates into anhydrous borax, Na2B4O7. We can see that borax has lots of water of crystallization, and along with anhydrous borax, 10 water molecules are also formed. So this illustrates the dehydration process of borax when heated, releasing water. Now we have the next reaction. It shows anhydrous borax, Na2B4O7, decomposing into sodium metaborate, 2NaBO2, and boric anhydride, B2O3. This is the thermal decomposition reaction. When we heat, anhydrous borax decomposes into two products, sodium metaborate, NaBO2, and boric anhydride, B2O3. So this glassy bead is made up of sodium metaborate and boric anhydride. Now moving on to next question. In the borax bead test of cobalt 2 plus, that is CO2 plus, the blue color observed in the bead is caused by the formation of which of the following compound? So we have four options given to us. Option A is B2O3. Option B is CO3B2. Option C is COBO2 whole twice. And option D is COO. So after doing this question, we will have the understanding of the borax bead test and the characteristic reactions of cobalt 2 plus ions as well in this test. Let's move toward the solution. So the correct answer is option C, COBO2 whole twice. In the borax bead test, the deep blue color of the bead when testing for CO2 plus is due to the formation of cobalt metaborate. And what is the chemical formula of cobalt metaborate? It is COBO2 whole twice. This occurs when cobalt ions react with boric anhydride and sodium metaborate formed from the heated borax. So here we have the reaction. The reaction shows the formation of cobalt 2 metaborate. What is the oxidation state of cobalt in cobalt metaborate? It is +2. So it is a blue glassy bead. So COO, that is cobalt oxide, react with B2O3 to produce COBO2 whole twice. The blue color indicates the presence of cobalt ions in the structure. So now moving on to next question. A solution of metal ion when reacted with potassium iodide, that is Ki, forms a red precipitate. that dissolve in excess Ki to produce a colorless solution. Additionally, when the metal ion solution is treated with solution of cobalt to thiocyanate, it results in the formation of a deep blue crystalline precipitate. Based on these observations, which metal ion is being referred to? So, four options are given to us. Option A is Pb2 plus, option B is He2 plus, option C is Cu2 plus, and option D is CO2 plus, that is cobalt 2 plus. Let's move on to the solution. The correct answer is option B, which is He2 plus. So this is the metal ion. So here we have the reaction taking place between mercury 2 ions and iodide ions, He2 plus and iodide ions. So He2 plus react with two iodide ions to form a red precipitate of mercury iodide, HeI2. The reaction is used to detect He2 plus ions in solution. The reaction shows the formation of a colorless complex ion, HgI4 2 minus. When excess iodide ions I minus react with mercury 2 iodide, that is HgI2. The reaction is a complexation process where I minus acting as a ligand and it gets coordinated to He2 plus, resulting in a stable colorless complex. So this reaction shows mercury 2 ions reacting with cobalt 2 thiocyanate to form a blue crystalline precipitate of COHG SCN whole 4. The thiocyanate ion, which is HCN minus, acts as a ligand and forms a complex with He2 plus, as we can see in the equation. The precipitate forms due to the low solubility of COHG HCN whole 4. This is blue crystalline precipitate plus CO2 plus. So CO2 plus is the byproduct here. So metal ion is He2 plus. This is our correct option. Option B. Now moving on to question number 7. So if Fe3 plus and Cr3 plus both are present in group 3 of qualitative analysis, then distinction can be made by. So how can we distinguish between them? Four options are given to us. Option A is addition of NH4OH in the presence of NH4Cl when only FeOH whole thrice is precipitated. Option B is addition of NH4OH in the presence of NH4Cl when CrOH whole thrice and FeOH whole thrice both are precipitated on an adding Pr to water and NaOH, CrOH whole 3 dissolves. Option C is precipitate of CH, a CrOH whole thrice and FeOH whole thrice as obtained in B are treated with Conc HCl when only FeOH whole thrice, that is ferric oxide, a ferric hydroxide dissolves. Or option D, both B and C. Let's move toward the solution. So correct answer is option D, both B and C. To separate Fe3 plus and Cr3 plus, ammonium chloride and ammonium hydroxide are added slowly and it produces ammonia. This raises the pH, causing both ions to precipitate as hydroxide. The smell of ammonia confirms the presence and it confirms the reaction, and precipitates can then be separated based on their solubility differences. To identify Cr3 plus, precipitate is treated with NaOH and Br2 water, that is bromine. A yellow coloration confirms the presence of Cr3 plus, that is chromium ions. This reaction shows the characteristic behavior of chromium ions in basic condition with bromine water. The reaction shows sodium hydroxide reacting with bromine to form sodium hypobromite, sodium bromide and water. This is a disproportionation reaction where Bromine is both oxidized and reduced. Here, Br2 is getting both oxidized and reduced, and it is forming NaBrO and NaBr. The reaction NaBrO producing NaBr plus O shows the decomposition of sodium hypobromide into sodium bromide and a nascent oxygen atom, free oxygen atom. This process releases elemental oxygen, and we know this is highly reactive. This is highly unstable as well as reactive. Now we have the reaction. This reaction shows chromium 3 hydroxide reacting with sodium hydroxide and oxygen to form sodium chromate and water. So Cr3 plus is oxidized to Cr6 plus. The solution is acidified to ensure proper conditions, then treated with lead acetate. This reaction shows sodium chromate reacting with lead 2 acetate to form a yellow precipitate of lead chromate, PbCrO4. The sodium ions combine with acetate ions, that is CS3COO minus, to form sodium acetate, CS3COO minus Na plus. The equation illustrates a double displacement reaction where soluble reactants form an insoluble product. So correct option is option D, both B and C. So that's all for today's chemistry session. Thank you.
everyone. So, in today's lecture, we will cover probability theory. Okay, so first we discuss some concept of probability, and then we practice some question on probability. Okay, so at first, let's analyze this chapter for JEE Mains examination. So, according to last 5 year data, this chapter probability, the chapter weightage is 3.82%. Okay, and if we do year-wise analysis, so in the year 2024, total one question came from this chapter probability based on conditional probability. Okay, and we know that conditional probability, formula of conditional probability is probability of E given F is equal to probability of E intersection F by probability of F. Okay, in the 2023, again one question from the topic Bayes theorem, very important theorem for probability. Okay, so and in the 2022, again one question from the Bayes theorem, and in the 2021, one question from the conditional probability, and in the 2020, one question from the expectation. Okay, so at first, in today class, at first we will see what is sample space and event. Okay, so at first we define a sample space and then we define event for sample space. Okay, and we will examine types of events. Then we will learn what the probability of an event and what are important method and what are the approaches to find probability of an event. Okay, some important results that we can directly use in our question. Okay, then we will learn one additional probability theorem, addition theorem on probability. Okay, then we will understand concept of conditional probability. It means find a probability of event when a probability of some event is already occurred. Okay, so event of a probability A when event B is already occurred. So such kind of probability is called conditional probability. Okay, then we will study the theorem of total probability. Okay, and then we understand one important concept of probability that is called random variable. So what is random variable? We will also see that. And at the last, we will discuss Bernoulli trials and binomial distribution. Okay, so in today lecture, we are going to cover all of this and then we will practice some question on probability. Okay, so the first topic is sample space. Okay, so let's start with sample space and event. So what is sample space? So sample space is just a set of all possible outcomes of a random experiment. So we do a random experiment and we collect all the possible outcomes of that random experiment. Then we get a set and that set is called sample space. Okay, and this set sample space is denoted by capital letter S. For example, as a random experiment, we are tossing a coin. So what are the possible outcomes? It can be head, it can be tail. So your sample space is head and tail. Okay, set S is head and tail. Rolling a die. So now our random experiment is we just rolling a die. So what can be the possible outcomes? It can be 1, 2, 3, 4, 5, 6. Okay, so sample space is the set of 1, 2, 3, 4, 5, and 6. Drawing a card from a pack of playing cards. So we know about the cards. Okay, so what are the possible outcomes? Collection of all its cards. That is your sample space for your random experiment, drawing a card from a pack of playing card. Okay, so sample space is nothing but sample space is the set of all possible outcomes of a random experiment. Okay, now let's come to event. So event is subset of S. Okay, sample space is the set of all possible outcomes, and when we take the subset of the sample space, that subset is your event. Okay, we define some condition, and according to the condition, let's consider A is the set element of this element of set which satisfy some condition. Okay, so all possible outcomes which satisfy that condition, all favorable possible outcomes we satisfy that condition, we collect, we make a set with these elements, and that is your event A, and that is your subset of S. Okay, so for example, if our die is rolled, okay, so now we have a die and we just rolling a die, that is your random experiment. So what is sample space? Set of all possible outcomes, so that can be 1, 2, 3, 4, 5, 6. So S is your 1, 2, 3, 4, 5, 6 is the sample space. Okay, now we define a event. Okay, so how we define? Getting an odd number. So what is your event? What does an event mean? So my event is we are getting a odd number, an odd number. Okay, so which are the elements of your set S which satisfy this condition? Okay, odd number, it mean it can be 1, 3, and 5. So 1, 3, and 5 are the outcomes of random experiment S, that is your die is rolled, that is satisfy a condition, that is getting an odd number. Okay, so we get A is 1, 3, 5, and this is your subset of S, so this is your event. Okay, so in case of coin, if you're tossing a coin, so a coin, it may be sample spaces head and tail, and we can define an event as getting head. So in that case, your event A is just a single element set, singleton set, that is head. And if you say the event is getting tail, then a singleton set B, that is your tail. So that's how we can define a sample space and an event. Okay, so if you want to understand, then at first we do a random experiment, then we collect all possible possible outcomes, that is a sample space, and then according to different condition we define different event. Okay, and according to that condition, we take a element from the set S which satisfy that condition, so we get a subset of S, that is your event. Okay, so in probability we have to find the probability of event. Okay, next is types of event. Okay, so now we have a sample space S, and we from the sample space S, subset of S, we get event. Okay, so we have different types of event. Okay, so first type is equally likely event. So the given events are said to be equally likely if none of them is expected to occur in preference to the other. Okay, so we understand this definition well, that such event which can them equally likely event, then their probability or expectation of occurring is neither more nor less compared to another event. Okay, that is, if the probability of any event occurring is neither more nor less than other, then such kind of events are called equally likely event. Okay, For example, we are rolling a die. Okay, so getting any number like getting a number 1, so probability of getting 1 is 1 by 6, and probability of getting 2 is again 1 by 6, probability of getting 3 is again 1 by 6. So all events are equally likely. That means if none of them is expected to occur in preference to other, all has same probability, then such kind of event are called equally likely event. Okay, next is mutually exclusive disjoint event. Okay, so now we look at the mutually exclusive disjoint event. So mutually means each other, with each other. Okay, so a set of event is said to be mutually exclusive if occurrence of one of them prevents or deny the occurrence of any of the remaining event. Okay, it means if we have two event, let's suppose we have event E1 and E2, then occurrence of one, that means occurrence of event E1, prevent or deny the occurrence of other event E2. That means these two event can never be occurred together. If one is occur, then E2 cannot be occur. That means E1 intersection E2 is phi. Then such kind of event is called mutually exclusive or disjoint event. Okay, that's like we are just same example rolling a die. Then we consider a event E1 as getting an odd number and event E2 as getting an even number. Then this both event are mutually exclusive event. If one event is occur, that means if we getting an odd number, then we cannot get even number. Okay, so occurrence of event E1 prevent or deny the occurrence of other E2 event. So this kind of events are called mutually exclusive event. In mathematical way, how we can write this? E1 intersection E2 is phi. So understand this, as we know, sample space is your set and events are subset of sample space. Okay, and elements of events are what? Which satisfy the condition of your event. Favorable outcomes which satisfy the condition of your events. Okay, so if two event subset of two, we take a two subset, that is two event for your sample space, and when we take the intersection, that is phi, that means there is no possible outcomes which satisfy the both condition. Okay, then such kinds of events are called mutually exclusive events. Okay, next is exhaustive event. So how we define this? So a set of event is said to be exhaustive if at least one of the event compulsory occur. Okay, so to understand this definition, let's suppose we have an event E1, E2, comma dash 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 En. So these events are called exhaustive event. If we take the union of this event, then we get a sample space. Okay, that means set of event is called exhaustive if at least one of them event compulsory occur. Okay, so if we draw a random experiment and we want to find then there must be an event that occur at least one of the event compulsory occur. Okay, then such kind of event are called exhaustive event which exhausts the sample space. Okay, so in a similar example that we take previously, rolling a die, and E1 is event you're getting an odd and E2 is event you're getting an even. So at least one of them already occur. If we get odd, then we cannot get even. And if we don't get an odd number, then we compulsorily get an even number. Then this two event, that is getting an odd number and getting an even number, when you take the union, what we get? We get a sample space. That means these two events are the event. When we combine this, we get your sample space. At least one of the event compulsory occur means we understand by this example. That means If we don't get an odd number, then we compulsorily get an even number. And if we don't get an even number, then we compulsorily get a odd number. So such kind of events are called exhaustive event. Okay. So for mutually exclusive, mathematical definition is if two events are mutually exclusive, then intersection is phi. And if the events are exhaustive, then unions of these events are your sample space. Okay. So there is a note. If the set of event E1, E2, En are mutually exclusive and exhaustive event, then now we combine both definition, mutually exclusive and exhaustive event. So the set of events E1, E2, comma dash dash En are mutually exclusive as well as exhaustive event if it satisfy the both condition. First condition that E1 EI intersection EJ is phi where I is not equal to J. So by this condition we satisfy the condition for mutually exclusive. Okay, and by the second condition, that is union of all EIs is your S, we satisfy the condition of exhaustive event. So if your set of events satisfy the both condition for the condition of mutually exclusive and exhaustive event, then your events are mutually exclusive as well as exhaustive events. Okay, clear? Next, complementary events. So what are complementary event? Okay, so let's understand this. So let's suppose we we do a random experiment and then we collect all the possible outcomes, that is your sample space, and we denote that sample space by S, and not let E be an event with some condition, and we take that is subset of your S. Then we define complementary event for event E. Okay, so as E is subset of S, then complement of E is S minus E. Okay, so S is called the complement of E. This EC, E complement is your complement of event E. Okay, so how to understand simply, we have a sample space S and E is an event of it. Then E means that it will be subset of S. Then we define E complement, that set in which the S minus E, that is all element of the sample space which are not in set E. So by removing them, the new set that is formed is called complementary event or complement of E. Okay, so if you understand completely what is complementary event, that means if we take the union of E and E complement, then what we get? So union of E and E complement is your entire sample space. Okay, that means the complementary event E and E complement are exhaustive events. In a similar way, by the definition, we clearly observe that E intersection E complement is phi. So these events are also mutually disjoint event. Okay. Next, probability of an event. So how we can find a probability of an event? Okay. So till now we understand a random experiment. What is sample space? Then we define events, that is subset of sample space. Then we also understand different types of events, mutually exclusive, disjoint, exhaustive, equally likely events, and also we understand what is complementary event. So now we have event. So how we can find the probability of this event? Okay. So we have a sample space. Let's suppose it has n elements. That means it has n points, all possible cases, all possible outcomes. Okay. So we draw a random experiment and all possible number of all possible outcomes is n. Okay, and then we define an event, and event has m points. Event A is a subset of your sample space, and it has total n possible outcomes, m possible outcome that satisfy the condition of event A. Okay, so now we have sample space with element n, and event A which has m elements, m points. Okay. Then probability of A. Okay. The probability of A is given by denoted by P of A, and the formula is m by n. All favorable outcomes will satisfy the condition of A by all possible outcomes. Okay, m by n. So that's how we find a probability of an event. Okay. Next is probability of A. This is the if we define a probability of A, then probability of any event is always lies between 0 and 1. It is always greater than equal to 0 and less than equal to 1. Okay, this is a property that satisfies a probability. Next is probability of sample space. Okay, so now we find probability of sample space. So according to definition of probability, S has n points and probability of S is n by n, that is 1. So probability of entire sample space is always 1 and probability of phi is 0. Okay, next is, okay, so now let's look the third point. Which is the probability of odds in favor of A? So how do we define this? So probability of odds in favor of A is equal to probability of A by probability of A complement. Okay, so that is the ratio. Probability of odds in favor of A is a ratio of probability of A by probability of A complement. So if we use the formula to find this value, we get m by n minus m. Okay, because we get probability of A is m by n and probability of A complement. If A has m points, then according to the complement definition of complement, A complement has n minus m element. So m by n, n minus m by n. So we get m by n minus m. Next is probability of odds in against A. So that is equal to probability of A complement by probability of A, that is n minus m by m. Okay, clear? So now let's look at some important result which we can use directly in our question. So first result, if n letter corresponding to n envelopes. Okay, so very important result. Now suppose we have total n letters and total n envelopes. Okay, and are placed in envelope at random. We place the letters in n envelope at random. Okay, then what are the results? First, probability that letters are in right envelope. Okay, so we have n letters, we have n envelopes, and for each letter we have defined a right envelope for that letter. Okay, but when we place them at random, it might be possible that they are placed in right envelope or they are not placed in right envelope. Okay, so the probability that letter in right envelope, that mean when we place the letter in envelope at random, what is the probability that we place the letter in right envelopes? So that is given by 1 by n factorial. Next, probability that at least one letter not in right envelope, that is given by 1 minus 1 by n factorial. Okay, and it might be possible that no letter are in right place. So what is the probability that no letter in right envelope is given by 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus dot 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 plus minus 1 the power n by into 1 by n factorial. Okay, and probability of exactly r letters in the right place. So that is given by 1 by r factorial into 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus dot 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 plus minus 1 the power n minus r into 1 by n minus r factorial. Okay, so there we have n letter and exactly r letters are in right envelope. So the probability of that is given by this formula. So these are the very important result if we have a question related to letters and envelope, so that we can directly apply this result to find our required probability. Okay. Next is addition theorem of probability. Okay. So let's understand what is this. So let's suppose we have two event A and B that is associated with a random experiment. So we drew a random experiment, we get a sample space, and we define two event, that is just event A and event B. Okay, then event of A union B, probability of A union B is given by probability of A plus probability of B minus probability of A intersection B. So this comes from the addition theorem of probability. What does it mean? Probability of A union B. Okay, so probability of either A or B, that is given by probability of A plus probability of B minus probability of A intersection B, that is probability of occurring both event A and event B. We subtract this probability of A intersection B so that we not double count this part probability of A intersection B, because when we add probability of A plus probability of B, we already count that probability of A intersection B. So we subtract this to get the exact value of probability of A union B. Okay. Next is, now if we have three event A, B and C that is associated with a random experiment, then probability of A union B union C, that is probability of occurrence of any of one, probability of A union B union C, that is probability of A or B or C. So that is given by probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of A intersection B intersection C. Okay, so this is the principle of inclusion and exclusion. Okay, union means at least one of the event is occur, and intersection means both event, both A and B event must be occur. Next is very important inequality. So what is this? If we have two event A and B, then probability of A is always greater than equal to probability of A intersection B, and probability of A union B is always greater than equal to probability of A, and probability of A plus B is always greater than equal to probability of A union B, and all are related. Okay, so probability of A intersection B is less than equal to probability of A, where probability of A is less than equal to probability of A union B, which is less than probability of A plus probability of B. Okay. Okay, so there is a important inequality, that is Wallace inequality. So what is this? It states that if A and B are two event, then probability of A intersection B is greater than equal to probability of A plus probability of B minus 1. Next, probability of A intersection B intersection C is greater than equal to probability of A plus probability of B plus probability of C minus 2. Okay, very important inequality. So let's look some note. First is probability of A complement intersection B complement. Okay, that means probability of neither A nor B. So that is given by 1 minus probability of A union B. Okay, so the probability of neither A nor B is given by 1 minus probability of at least 1. Okay, so we can prove this result by De Moivre's the De Moivre's theorem on set theory. So you can apply this theorem to prove this result. Second result is probability of A complement union B complement is equal to 1 minus probability of A intersection B. Okay. Next result, probability of A. So we define probability of A with the help of intersection of A and B and intersection of A and B complement. So probability of A is equal to probability of A intersection B plus probability of A intersection B complement. And probability of B is probability of B intersection A plus probability of B intersection A complement. If you understand this, that means if you want to find the probability of B, then that is equal to probability of when both event is occur. Probability of B intersection A plus probability of B when event A is not occurring. That is A complement. So that's how we can calculate probability of B. Okay. Now, probability of exactly one of E1 and E2 occur. Exactly one of. So, how we get this? So, at first understand the mathematical form of exactly of one of E1 and E2 occur. So, first, probability of E1 intersection E2 complement. That means, what does it mean? It means probability of event E1 when E2 is not occurring. E complement, E2 complement. Okay, intersection means both event occurring, and even intersection E2 complement means even occurring but E2 is not occurring, plus probability of even complement intersection E2. So this means E2 is happening but even is not. So that's how we can find probability of exactly one of E1 and E2 occur, and that is equal to, if we apply the above formulas, we get probability of E1 minus probability of E1 intersection E2 plus probability of E2 minus probability of E1 intersection E2. Okay. And from here we get probability of E1 plus probability of E2 minus 2 into probability of E1 intersection E2. So probability of exactly of one of event E1 or E2 occur is given by probability of E1 plus probability of E2 minus 2 times probability of E1 intersection E2. Okay. Next important result, probability of neither E1 nor E2. It means probability of happening neither E1 and not even E2. So that is given by probability of E1 complement intersection E2 complement. Okay. And that is 1 minus probability of E1 union E2. Okay. Now, next is conditional probability. So, let's suppose we have event A and B, and this two event is associated with a sample space of a random experiment. Then how can we define conditional probability of the event A given that B has occurred? So now we find a probability of an event when one event is already occurred. So how we denote this? Probability of event A by B. It means probability of event A when B is already occurred. Okay. So we have a sample space. We define an event. We define two event A and B, and we say B event is already occurred. Now find what is the probability of A. It can be that event A is dependent on event B, or it might be possible it does not depend upon B. So, so the conditional probability A given B is given by probability of A intersection B by probability of B, provided that probability of B is not equal to 0. So by this formula, we can find conditional probability, probability of A given B. Okay. Some properties on conditional probability. So first is, if S is your sample space and A and B are two events with this sample space, then probability of S given A. What is the probability of happening the sample space when A is already occurred? So if you apply the formula, you get probability of S intersection A, okay, as S your sample space and A is subset of S. So what is the value of S intersection A? That is again A. So we get probability of A by probability of A, and that is 1. Okay. So probability of S given A is equal to probability of A given A, that is 1. Next property, probability of A complement given B. That is, now we find probability of a complement of A when B is already occurred. So that is equal to 1 minus probability of event A when B is already occurred. Clear? So main thing on conditional probability is that conditional probability is used when we have to find a probability of an event where one event is already occurred. Okay. Next is multiplication theorem of probability. So if we have two event A and B that is associated with a random experiment, then probability of A intersection B, that is equal to probability of A into probability of B given A, or it can be equal to probability of B into probability of A given B. Let's suppose that is A intersection B means the events are happening in a sequence. So let's suppose A is already occurred, then we have to find then B. So probability of A intersection B. So now we have to find probability of occurrence of both. So how we get this? Probability of A into probability of B given A. That means probability of A, that is the probability of A into we multiply with probability of event B when A is already occurred. So that using this we can find the occurrence of both event. In a similar way, if B is occurred then A, then what is the formula? Probability of B into probability of A given B. Okay. So this is come from conditional probability, and is provided that probability of A is not equal to 0 and probability of B not equal to 0. So this is your multiplication theorem. Next is independent events. Okay. So two events are said to be independent if the occurrence of one does not depend upon the other. Okay. So if we have two event, let's suppose E1 and E2, and let E1 is already occur, but occurrence of E1 does not affect the occurrence of E2. So such kind of events are called independent event. Okay. So let's suppose we have n events E1, E2, dot 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 En. Then if we take the probability of intersection of all these events, that is probability of E1 intersection E2, intersection E3, intersection dot 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 intersection En. As these all events are independent event, that means occurrence of one does not affect the occurrence of other. It does not depend upon the other. So if you apply the multiplication rule of probability, as the occurrence of one does not depend on other, so that we directly get is equal to probability of E1 into probability of E2 dot into probability of dot 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 probability of En. So we just need to multiply all the probability to get the probability of intersection if your events are independent. Okay. Next is important result, very important result. If your two events are independent, let's suppose E and F are independent, then the pairs E and F complement, E complement and F, E complement and F complement are also independent. Okay. So if you have your E and F and both are event are independent, then all other pair E and F complement, E complement and F, and E complement F complement are also independent. So main important result is if two event E1 and E2 are independent, that means occurrence of E1 does not depend the occurrence of E2. Then if we want to find the probability of intersection of E1 and E2, then we just need to multiply the probability of E1 and probability of E2. Okay. Next is theorem of total probability. So if an event A can occur with one of the n mutually exclusive and exhaustive event B1, B2, comma dot 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 Bn, and the probability of P, probability of A given B1, probability of A given B2, sorry, probability of A given B1, probability of A given B2, comma dot dot, probability of A given Bn are known. Then what is the probability of A? Okay, so that is given by probability of A is equal to summation from I is equal to 1 to n, probability of Bi into probability of A given Bi. Okay, so what is the meaning of total probability? So probability A, but your event A depend on a prior stage of event Bi. Okay, that is your partition of probability. So Bi is a partition of probability. So your event A is depend on the prior events Bi's, and your event Bi is already occurred. Okay, so A is your event, first thing. Second thing, A depend on the prior events Bi's. Okay, second thing, these prior events Bi's are mutually exclusive and exhaustive event. That means Bi intersection B's is phi, and if you take all union of all Bi's, we get your sample space S. Then we also know that probability of A given B1, probability of A given B2, conditional probability. These are the conditional probability. Probability of A given Bn. Okay. Then what is the probability? So that probability is e- is equal to the summation of all the probability of Bi's into probability of A given Bi's. Okay. So probability of A intersection B1 plus probability of A intersection B2 plus probability of dot 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 probability of A intersection Bn. So that is your rule of total probability. Next is Bayes theorem. So it is also very important theorem on probability. So Bayes theorem is used for inverse probability. For example, what is the we are asked for what is the probability that a person has a disease given that result was positive. Okay, so if we want to calculate such kind of probability where we have to reverse the condition. Okay, we want to calculate probability of B given AI to probability of AI given B, then we use Bayes theorem. Okay, so let the sample space S be union of n non-empty disjoint subsets, mutually exclusive and exhaustive event. So these are the events A1, A2, dot 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 AN, which are mutually exclusive and exhaustive. That means AI intersection is phi for all I not equal to j, and if you take the union of all the events, we get your sample space. Okay. Next, for any event B such that B is equal to A1 intersection B union A2 intersection B union dot 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 union AN intersection B. So we calculate the probability of B by using the theorem of total probability. Okay. So what is the probability of B? That is equal to summation from I is equal to 1 to n probability of A1 AI into probability of B given AI. Okay. Then what is the probability of AI given B? We reverse the probability. We have a probability that probability of B given AI. That means what is the probability of event B when AI is occurred. But when we want to find a particular probability that what is the probability of AI when B is already occurred, then we apply the Bayes theorem, and that is probability of AI given B is equal to probability of AI intersection B by probability of B, and that is equal to probability of AI into probability of B given AI by what is the probability of B? Apply the theorem of total probability. So we get summation I is equal to 1 to n probability of AI into probability of B given AI. Okay. Next. So now we discuss random variable. So what is random variable? So random variable is a function it is a real valued function. Okay, so random variable is your real valued function. That means it gives a real number. Then what is your domain for this function? So for function random variable, the domain is your sample space. Okay, so if we draw a random experiment, then we have a sample space. Sample space is sample of all possible outcomes. Then we can define random real valued function, which take the element from the sample space and give a value, real value. So that is your random variable. So random variable is a real valued function whose domain is the sample space. Okay, so how we understand this? Let's suppose we do a random experiment. We toss a coin. So sample space is head and tail. Okay, then we define a random variable, a real valued function, define as x. Let's take x is your random variable. So x is number of heads as your random variable. So it take element from a sample space. Sample space only two element, head and tail. So x at h as x your function. So x at h. So for your h, number of head is 1. So x at h is 1. And x of t, x is a function of number of head. And for even t, there is no head. So x of t is 0. So 1 and 0 is real value. So that's how we can define random variable. So random variable is usually denoted by capital letter X, Y, and Z, and so on. Okay, now we understand what is probability distribution for a random variable. Okay, so let's suppose we have a random variable X, and the value of X are the real value. Let's suppose the values of X are X1, X2, X3, comma dot 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 Xn, and the probability of each Xi is Pi's. That in probability of X is equal to Xi is Pi. So we get the respective probability as P1, comma P2, comma P3, dot 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 Pn. Then x, the value of x can be x1, x2, x3, dot 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 xn, and probability for each respective values xi is your p1, p2, p3, dot 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 pn. So this known as probability distribution of random variable x. Okay. Next is when the probability distribution is defined. So now we have a random variable x, and the probability distribution of this random variable is defined only if, let's suppose, the various values of random variable is x1, x2, x3, dot 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 xn, and respective probability with these values are p1, p2, p3, comma dot 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 pn. So if this satisfy that probability of this pi is greater than 0, and if we take the sum of all this pi, we get 1, then your probability distribution is defined. So probability distribution for any random variable x is defined only if the values of random variable is xi's and the respective probability is pi's. So if all the pi's is greater than 0, and if you take the sum of all pi's, if you get 1, then in this case probability distribution is defined. Okay, now what is mean? So if the random variable x, assume value x1, x2, and x3 dot 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 xn with respective probabilities p1, p2, p3 dot 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 pn, then mean that is noted by x bar, that is defined as x bar is equal to p1 x1 plus p2 x2 plus dot 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 pi xi. So we multiply the value x1 with their respective probability p1, and they do put the same p1 x1 plus p2 x2 and take the sum, and that is your mean. Okay, so mean is equal to summation I is equal to 1 to n pi xi. Okay, and this mean of the random variable is also known as mathematical expectation, and that is denoted by e of x. Okay, next is variance. So if a random variable x, assume value x1, x2 dot 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 x3 dot 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 xn with respective probability p1, p2 dot 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 pn, then variance of x is defined by this formula: summation I is equal to 1 to n pi xi square minus summation I is equal to 1 to n pi xi whole square. In terms of expectation it can be written as e of x square minus expectation of x whole square. Clear? So that is your variance for a random variable. So next is Bernoulli trials. So what is Bernoulli trial? So trials of a random experiment are called Bernoulli trials if they satisfy following condition. First is there should be finite number of trials. Trials should be independent, and each trial has exactly two outcomes: either its success or its failure. And probability of success or failure remains same in each trial. Then these trials are called Bernoulli trials. So with the help of Bernoulli trials, we define binomial distribution. So we can relate this Bernoulli trials with tossing a coin. So if you toss a coin, it can be head and tail. We finite number of trials. We finitely times we tossing a coin, and trials should be independent. Tossing a coin is independent with respect to other trial. And if we take head, we consider it as success. If we take tail, we consider it as failure. And probability of head and success is always remains same, that is 1 by 2. Okay, if you have unbiased coin. Now with the help of binomial trial, we define our binomial distribution. So what is binomial distribution? Probability of r success in n independent binomial trial. So how many times we just example, how many times we toss a coin? N times, n independent binomial trials. So number of r success, number of r head, okay, that is noted by probability of x is equal to r, and it is given by formula for NCR PR q the power n minus r, where p is probability of success and q is probability of failure, and p plus q is equal to 1. Okay, and if we calculate the mean for this binomial distribution, that is n into p, variance is n into p into q, and one important thing, mean is always greater than variance. Clear? So this is your theory part. Now you'll practice some question. So just wait for a moment. Okay, first question. If three distinct numbers are chosen randomly from the first 100 natural number, then the probability that all three of them are divisible by both 2 and 3 is. Okay, so in total we have 100 natural number. Okay, and from this 100 number, how many numbers? Total three distinct number we are choosing from this 100 natural number and randomly. Okay, then in this question we are asked for the probability that all three of them are divisible by both 2 and 3. So what number we are chosen? They are divisible by both 2 and 3. Okay, so what is the probability for this? Option A 4 by 55, option B 4 by 35, option C 4 by 33, option D 4 by 1155. Okay, so in total we have how many numbers? 100 natural number. First 100 natural number. It means 1, 2, 3, dot 100. And from this 100 number, we choose three distinct number. And what is the condition? We condition is that these number are divisible by 2 and 3. So first count the number which numbers are divisible by 2 and 3. How we can count this? Okay, so as a hint, use the property of arithmetic progression to count the number, total number, and then solve this question. Okay, so try this question. Take your time. Okay, anyone? Which option is correct? Okay, let's solve. So correct answer is option D, that is 4 by 1155. So how we get this? So one important observation, if any number is divisible by 2 and 3, then it is also divisible by 6. Clear? And how, what is the number of selection? How we use combination to select number from different numbers? So we have n distinct thing. So selection of r distinct thing is NCR. Clear? And what is probability of A? That is number of cases that satisfy your event A by total number of possible cases. Okay, that is NS. So first thing, we have total 100 natural number, and from there we selecting three numbers. So number of S, that is number of element in sample space, is 100 C3 total number. And now what is your event? Event is all three of them are divisible by 2 and 3. That means this number are divisible by 6. Okay. So now we calculate number of number of numbers which are divisible by 6 and less than 100 and greater than 1. So first number is that is divisible by 6, between 1 and 100 is 6. Then next is 12, next is 18, comma dot dot dot. Last number is 96. Clear? We can find this first and last number and some numbers. So if you observe, this number are in AP. Okay, so if numbers are in AP, then we can calculate the number of uh, elements present on the AP by using the formula. We have the formula n is equal to a plus n minus 1d. N is the last element, n is the number of element present, so we have to calculate that n. So here n is 96, a is 6, and n minus d, and d is common difference, that is 6. So by using the formula we get the value n, that is 16. Okay, so out of 16 we have to select 3, that is your NA. So NE is 16 C3. Total 16 numbers are between 1 to 100 that are divisible by 6. And out of this 16 number we have to select 3. So NA is 16 C3. So required probability is NA by NS, that is 16 C3 by 100 C3. And if you solve this combination you get 4 by 1155. Clear? Simple. Okay, next question. If the letter of the word mathematics are arranged arbitrarily, the probability that C comes before E, E before H, H before I, and I before S is option A 1 by 75, option B 1 by 24, option C 1 by 120, and option D 1 by 720. Okay, so in this question, we have a word mathematics, and we arranged words like we get another word by using this using these letters. We just arrange the letters to get new word. Okay. Now we have to find a probability. Which event? Event is that C comes before E. Okay. E before H. That is C, then E, then H. H before I. H, then I, and I before S. Okay, so we have to find the probability of an event where this is your required condition. That is what we arranged by using the letter of mathematics. This is the required condition. This is the event. Okay, so which option is correct? Try this question. Use the concept of permutation to solve this question. What can be the number of possible words that can we make with the help of words in mathematics? First thing is this, that is your number of element in sample space. Okay, and then we have to also count the number of element which satisfy with number of words we satisfy the condition of the event, that is E comes before E come before H come before I before S, that is C E H I S. We probably fix the position of C E H I S. Okay, so then what are the number of words that can be arranged with this condition by using the letters of mathematics? That is your number of element in your event E, if you define event E with this help, with this condition. Okay, and then simply apply the formula or probability to get the answer. Okay, so try this question. Anyone? Which option is correct? Okay, let's solve. Let's solve together. So correct answer is option C, that is 1 by 120. So how we get this? So the concept of permutation that we use here is that the number of permutation, we just arrange the letters. Okay, and in this case, to count the number of letters, we use permutation. So number of permutation of n things taken all at a time. Okay, so we have the word mathematics, and to arrange we take all the letters of mathematics to get a new word. Okay, and p of them are similar and of one type. So out of this n things, there are p things that are similar, and q of them are similar and of another type, and there is another type of which thing, and q of them are similar. In the same way, r of them are similar of the third type, and remaining n minus p plus q plus r. Then in this case, number of permutations given by n factorial by p factorial into q factorial into r factorial. As in, if you see the later word mathematics, so there are letter m two times. Okay, so to find the permutation, we must divide with the 2 factorial. Okay, we also have other letter like a 2 times, t two times. So these are identical, similar type. So to find the number of permutation to arrangement of these later, we have to divide with the factorial of identical number of terms which are identical. Okay, and probability of A is given by number of element in A by number of S, number of element in S. Okay, so total number of arrangement, that is your NS. So total we have 11 letters, and we arrange this letter arbitrarily to get our words. And here M, T and A are the letter which occur 2 times. So we divide by the 2 factorial into 2 factorial into 2 factorial to get the total number of arrangement. Okay, that is 11 factorial by 8. Next, what is the event? Event is C comes before E, E before H before I before S. Okay, so number of arrangement in which this condition is satisfied. That means this event is satisfied. So now we count the number of outcome, number of words we satisfy the event. Okay, so that is given by 11C5. From 11 we selecting 5 letter and then remaining 6 letter. That is 6 factorial by 2 factorial into 2 factorial into 2 factorial. Remaining 6 letter are M, A, T, M, A, T, 2M, 2A, 2T. So we get 6 factorial by 2 factorial, 2 factorial, 2 factorial. And for the word CEHIS, we chose 5. So 11 C 5. So we get 11 factorial by 8 minus 5 factorial. We just use the formula of 11C5 and simplify. We get 11 factorial by 8 into 5 factorial. We can understand this in different way, as we have what CEHIS are in together. So we can consider this letter are identical letter, similar letter. So total 5 letters. So if we take it as similar letter, because all these words are come together in our words, so total 5 letter. So we have to divide number of 11 factorial by 5 factorial. So we get 11 factorial by 8 into 5 factorial. Okay, because when we arrange total 5 letter, when we arrange, there is only one case where we get the word CEHIS. Okay, so we have to divide with 5 factorial. So where 11C5 represents the selection of 5 position out of 11 position to place our word CEHIS in that order. Okay, so required probability is NA by NS. So we get ln factorial by 8 into 5 factorial divided by ln factorial by 8, and when we solve we get 1 by 5 factorial, that is 1 by 120. Okay, next question. If A and B are two event, then the probability that exactly one of them occur is given by. So in this question we have two event A and B, and we have to find the probability that exactly one of them occur. Okay, so option A, probability of A plus probability of B minus 2 into probability of A intersection B. Option B, probability of A intersection B complement minus probability of A complement intersection B. Option C, probability of A union B plus probability of A intersection B. Option D, probability of A complement plus probability of B complement plus 2 into probability of A complement intersection B complement. Okay, so try this question. How we write the sentence that exactly one of them is occur in the terms of using the operation on set. Most important thing to calculate the probability is that if the words are given in words, then how you can calculate in the mathematical expression, how we convert this. If you convert it, then we can easily calculate. Okay, so let's calculate. So correct answer is option A, that is probability of A plus probability of B minus 2 times probability of A intersection B. So how we get this? So we have the formula that we use here is that probability of either only X or only Y occur is given by probability of X intersection Y complement union Y intersection X complement. Okay, and probability of X union Y is your probability of X plus probability of Y if X intersection Y is 5, because the formula is probability of X and Y is probability of X plus probability of Y minus probability of X intersection Y, but has here X and Y is disjoint, so we get probability of X plus probability of Y. And probability of X is, the formula is probability of X is probability of X intersection Y complement plus probability of X intersection Y. Okay, so in this question we have to calculate the probability that exactly one of them occur. Okay, so that is equal to probability of A intersection B complement union B intersection A complement. Okay, so apply the formula. we get probability of A intersection B complement, probability of B intersection A complement. And from here, when we apply the formula of probability of A intersection B complement, we get probability of A plus probability of B minus 2 times probability of A intersection B. So correct answer is option A. So next question. The probability that at least one of the event A and B occur is 3 by 5. If A and B occur simultaneously with probability 1 by 5, then probability of A complement, probability of B complement is equal to option A 2 by 5, option B 4 by 5, option C 6 by 5, and option D 7 by 5. Okay, so take this question as homework, take the screenshot, okay, and try this question. So first convert the word into the form of sets, in the form of union, in form of intersection by using complement of A, complement of B, and then try to solve this question. Okay, so that's all for today. Any doubt? Okay then, thank you.
Hello students, in today's lecture we are going to learn about semiconductor electronics, and logic gates. All right, this is our disclaimer. So firstly, in this lecture we will study uh, energy bands in solids. Then we will discuss about semiconductors. After that, we will study superconductors. Then we will study types of extrinsic semiconductor. Then we will discuss semiconductor diode. After that, we will see mobility of charge carriers. Then we will discuss IV characteristics of semiconductor diode in forward and reverse bias. Then we will discuss diode as a rectifier. Then we will discuss Zener diode. All right. Then light emitting diode. Then we will discuss photodiode. And last we will see solar cell. Okay. So these are the topics which we will discuss in today's lecture. All right, everyone. So students, our first concept is energy bands in solids. So we can say, according to band theory of solids, when atoms come together to form a crystalline solid, the balanced electrons of neighboring atoms interact with each other. Why? Because of this interaction, the discrete energy levels that electrons occupy in isolated atoms broaden into continuous ranges of energy called energy bands. Okay, instead of having sharp individual energy levels. So electrons in a solid occupy these bands. All right. Uh, the energy bands in solids are mainly divided into three types. First, valence band. Second, conduction band. And third, forbidden band, or we can say energy gap. All right. So first, we will discuss about valence band. The valence band is formed uh, from the energy levels of the valence electrons that are actually present in the atoms. Okay, so at absolute zero temperature, means 0 Kelvin, this band is usually completely filled with electrons. Since the valence band is full, the electrons in this band cannot easily gain energy from an external extrinsic field to move freely and conduct electricity. All right. So the highest energy levels that electrons occupy in the valence band at 0 Kelvin is called Fermi energy level. All right. Clear? Next, we will discuss conduction band. So right above the valence band lies the conduction band. All right. This band consists of energy levels uh, just higher than those in the valence band. In conduction band, uh, we can say electrons that occupy the conduction band are free to move throughout the solid. Okay, which means they can easily respond to an external electric field and conduct electricity. Students, these electrons are uh, often referred to as a free electrons. Okay, because they are not bound to any particular atom. And third band, forbidden band. Okay, So if we talk about forbidden band, so we can say uh, separating the valence band and conduction band is a range of energy levels that electrons cannot occupy, called the forbidden band or energy gap. Okay, students, this energy gap is denoted by Eg, okay, E capital, G small, and is crucial in determining the electrical behavior of material. Okay, so in forbidden band, the width of this forbidden gap varies for different substances and is given by the difference in energy between the bottom of the conduction band and the top of the valence band. Okay, if you want to find out the Eg, so it will be what? It will be E conduction band minus E valence band. Okay, or if the gap Eg is very small, or we can say zero. Okay, so the material behaves as a conductor, and if the gap is moderate, the material is a semiconductor, and if the gap is large, the material acts as an insulator. All right, so this is the all about the valence band, conduction band, and forbidden band. If you have any doubt, please ask everyone. Clear? All right. Now, students, in semiconducting solids, the valence band is completely filled with electrons. Okay, and whereas the conduction band is completely empty at absolute zero temperature. So the energy gap between these two bands denoted by Ig. We know this, and Ig is small enough to allow electrons to jump from valence band to the conduction band. And at higher temperatures, okay, so typically this energy gap satisfy Eg is less than 3 electron volt. Okay, Eg is less than 3 electron volt. All right, this one. Because of this small gap, semiconductor behave as insulators at absolute zero, but can conduct electricity when thermal energy excites electrons across the gap. Okay, and if we talk about the pure semiconductor, so we can say a pure semiconductor that has not been mixed with any impurities, okay, is called an intrinsic semiconductor. Okay, for example, um, germanium and silicon, and their energy gaps are for germanium Eg equal to 0.72 electron volt, okay, and for silicon Eg equal to 1.1 electron volt, okay. These intrinsic materials show electrical conductivity due to solely to electrons excited thermally from valence band to the conduction band. Okay, and if we talk about the electrical conductivity in pure semiconductor, so we can say the electrical conductivity of a pure semiconductor is quite low. Why? Why quite low? Because only a small number of electrons have enough energy to cross the band gap. Okay, so how we can increase the conductivity? Think about it. So to increase conductivity, the semiconductor is doped with a controlled amount of impurity atoms. Typically, one impurity atom is every 10 to the power 5 or 10 to the power 6. atoms of the pure semiconductor. All right, students, this process creates an extrinsic semiconductor. So the impurities introduce additional charge carriers like electrons or holes, which greatly enhance the conductivity. Okay, and if we talk about the number of electrons, so we can say the number of electrons denoted by n that are thermally excited from the valence band to the conduction band depends on the temperature T and the energy gap Eg. Okay, so it is given by this relation. All right, where K is what? K is Boltzmann constant, T is the absolute temperature, A is constant. And this formula shows that as temperature T increases, more electrons gain sufficient energy to jump across the band gap, increasing the electrical conductivity. Superconductors. So students, this topic only for information. Okay. So if we, when certain metals are cooled down below a specific temperature known as critical temperature, okay, so uh, their electrical resistance abruptly drops to zero, and this remarkable state in which a material exhibits zero electrical resistance is called superconductivity. Okay, so in these states, uh, or we can say metals that exhibit this zero resistance properly below their critical temperature are called superconductors. So in the superconducting state, electrical current can flow without any energy loss, which has important technology applications. All right. So different metals have different critical temperatures at which they become superconductors. Okay. So if we talk about examples, so we can say mercury becomes superconducting at 4.2 Kelvin, whereas lead becomes superconducting at 7.25 Kelvin, and niobium becomes superconducting at Tc uh, equal to 9.2 Kelvin. Okay, clear? Now we will discuss about the types of extrinsic semiconductor. Okay, so students, extrinsic semiconductors are classified based on the type of doping impurities added. So there are two main types, N-type and P-type semiconductors. All right. So here we focus on the N-type semiconductor. So here a question arises how we can prepare N-type semiconductor. So students, to prepare an N-type semiconductor, a pentavalent impurity. Okay, pentavalent impurity means an element with 5 valence electrons. Okay, so a pentavalent impurity such as phosphorus, arsenic, or antimony is added as a dopant to a pure semiconductor like silicon or germanium. Okay, these impurities introduce extra electrons into the crystal lattice. Crystal lattice. All right. So the pentavalent impurity is called a donor impurity because each dopant atom donates one free electron to the semiconductor. Okay, and this increases the number of electrons available for conduction. So in an n-type semiconductor, the concentration of free electrons Ne is much greater than the concentration of holes NH. Okay, that is Ne is greater than NH. All right, it means electrons are the majority charge carriers and holes are the minority charge carriers. Okay, So the product of the electrons concentration Ng and the whole concentration uh, NH, electron concentration here Ne, okay, and whole concentration NH. So when we take the product, okay, so it will be a constant and equal to the square of the intrinsic current carriers. All right. So Ne into NH equal to Ni square. So despite the excess electrons in the n-type semiconductor remains electrically neutral overall and it is not negatively charged. And if we talk about their electrical conductivity, so we can say the electrical conductivity sigma of an n-type semiconductor depends mainly on the number of free electrons and their mobility. Okay, and it can be approximated as sigma is approximate equal to Ne mu E into E. Okay, where Ne is the number of density of majority carriers and mu E is the mobility of electrons here. All right. Now the second type of semiconductor, p-type semiconductor. All right. So again here a question arises, uh, how we can prepare p-type semiconductor? Tell me. So to prepare a p-type semiconductor, a trivalent impurity is introduced into a pure semiconductor such as silicon or germanium. Okay. For examples, uh, trivalent impurities include boron, aluminum, indium, gallium. Okay, so these impurities have 3 valence electrons, which is one less than the 4 valence electrons of silicon or germanium. All right, so such trivalent impurities are called acceptor impurities. Why? Because they tend to accept an electron from the crystal lattice to complete their valence shell. So when an acceptor impurity atom captures an electron, it effectively creates a hole in the lattice, which can move and act as a positive charge carriers. Therefore, each dopant atom effectively provides one hole. All right. So in a p-type semiconductor, the hole concentration NH is much greater than the electron concentration Ne. So we can say NH is greater than Ne. Okay, which means that holes are the majority charge carriers and electrons are the minority charge carriers. Okay, and the product of hole concentration and the electron concentration uh, satisfy the intrinsic carrier relation, and that relation is NH into Ne equal to Ni square, where Ni is the intrinsic carrier concentration. Clear everyone? So despite the predominance of holes, the p-type semiconductor remains electrically neutral overall and is not positively charged. Okay, so the number of free charge carriers in a semiconductor, including holes in p-type material, varies with temperature, approximately T to the power 3 by 2. This means that a temperature increases, more charge carriers are generated, enhancing the conductivity. And the electrical conductivity sigma of a p-type semiconductor depends mainly on the hole concentration NH, the hole mobility mu h, and the charge of an electron E, and it is approximated sigma is approximately equal to NH into mu E H into E. All right, and all the formulas are very important for the exam. Clear everyone? Now we will discuss semiconductor diode. So listen carefully. A PN junction is created by joining a small p-type semiconductor crystal with a small n-type semiconductor crystal without using any other binding material between them. Alright. So when the PN junction is formed, electrons from the N region diffuse across the junction into the P region, and holes from the P region diffuse into the N region. Okay, and this movement of charge carriers, listen carefully, this movement of charge carriers occurs due to concentration gradients. So as the electrons and holes moves across the junction, the electrical neutrality of both the N and P regions is disturbed near the junction. Okay, so here uh, a thin layer of immobile negatively charged ions forms on P side close to the junction, while a layer of immobile positively charged ions forms on N side near the junction. So these ions are the results of electrons and holes leaving their original regions. And the region containing these immobile ions where the free charge carriers are uh, we can say free charge carriers are depleted is called depletion layer. Okay, and the thickness of depletion layer is approximately of the order of 10 to the power minus 6. And if we talk about the potential difference, so we can say due to diffusion of electrons and holes, a potential difference develops across the p-n junction, and this potential difference is called the potential barrier VB. Okay, so sometimes thought as the electromotive force known as EMF of a fictitious battery that opposes further diffusion. Okay, and for germanium diode barrier, uh, potential is 0.3 volt, but for silicon diode, its value is 0.7 volt. All right. So uh, if we talk about barrier, so we can see the barrier creates an electric field at the junction which is on the order of 10 to the power 5 volt per meter. Now let's see mobility of charge carriers. All right. So the mobility of a charge carriers in a semiconductor is defined as the velocity that the carrier gains per unit electric field applied. Students, in other words, a mobility mu means how quickly an electron or holes moves through the material when subjected to an electric field. Okay, so mathematically this is expressed as mu equal to Vd divided by E. Okay, so here Vd is the drift velocity of the charge carriers and E is the applied electric field. All right. And if we talk about the current, so we can say the total current I flowing through a semiconductor is the sum of the electron I's E and the whole current IH. Okay, so each type of charge carriers contributes to the current based on its concentration, charge, velocity, and the cross-sectional area A of the semiconductor. This is given by I equal to IE plus IH is equal to E into A into Ne into Ve plus Nh into Vh. Okay, where E is the charge of an electron, Ne and Nh are the concentrations of electrons and holes respectively. Ve and Vh are their respective drift velocities. Clear everyone? Now we will discuss about the conductivity, and this is most important concept for the exam. Okay, so if we talk about the conductivity, so we can say The conductivity sigma of a semiconductor relates the current density J to the electric field E. It can be expressed as sigma equal to J by E is equal to I upon AE, which is equal to E into NE mu E plus NH mu H. Here J is the current density defined as the current per unit cross-sectional area. Okay, mu E and mu H are the mobilities of electrons and holes respectively, and Ne and Nh are the electrons and holes concentrations. E is the charge of an electron. Clear everyone? So the current density J is also often written as J equal to N into Q into V. Okay, when N is the charge carrier concentration, Q is the charge of the carrier, usually E for electrons, and V is the drift velocity. Alright, now let's see IV characteristics of semiconductor diode in forward and reverse bias. Okay, so when an external voltage source is connected such that the P side of the PN junction is connected to the positive terminal of the voltage source and N side is connected to the negative terminal. Okay, so the junction is said to be forward biased. In this condition, the applied electric field E created by the external voltage opposes the built-in barrier electric field EB of the junction. So due to this opposition, the width of the depletion layer decreases because the external field reduces. Okay, so uh, the barrier that prevents charge carriers from crossing the junction. Okay, so when the applied voltage V, okay, applied voltage V uh, exceeds the barrier potential VB, that is V is greater than VV, a forward current begins to flow through the junction. Okay, and the resistance offered by the PN junction under forward bias is small, typically in the range of 10 to 50 ohm. Okay, so look at here in the diagram. Here, uh, this shows forward biased, reverse biased. Okay, so here, uh, in case of forward biased, there is a diffusion layer. Okay, and if the connections of the voltage source are reversed, such that the P side is connected to the negative terminal and the N side to the positive terminal of the battery. Okay, so the junction is said to be reverse biased. Look at here, this one. The junction is said to be reverse biased. And in the case of applied electric field E and the barrier electric field EB point in the same direction. Okay, so they add up, increasing the barrier. Okay, so because the electric field add, the width of the depletion layer increases, preventing current flow through the junction except for a very small leakage current. So this effectively blocks the flow of charge carriers, making the junction behave like an insulator. Okay, so when a PN junction is formed, okay, uh, a depletion layer is created at the interface between P and N types materials. Alright, so look at here. This is a PN junction. P type material this side and E type, N type. Okay, so uh, a depletion layer is created at the interface between P type and N type materials. So this depletion layer broadens. This depletion layer broadens and potential barrier across the junction becomes stronger. Okay, so as a result, only a few small leakage current can flow through the junction, and this leakage current is mainly due to minority charge carriers. Okay, here minority charge carriers electrons in p region and holes in the n region. Okay, and because of this junction resistance becomes extremely high, approximately of the order of 10 to the power 5 ohm. So in case of reverse bias students, so when a reverse bias voltage is applied to a PN junction, okay, here reverse bias, and this voltage becomes sufficiently high, around 25 volt, okay, or more, the reverse current suddenly increases sharply, okay, and this phenomena happens because the high reverse voltage cause a breakdown of the junction. So the voltage at which this sudden increase in current occurs is known as a breakdown voltage or avalanche voltage. Alright. So the PN junction can be seen as a voltage control switch. Under forward bias, when the P side is connected to the positive voltage and N side is negative, the junction acts like an on switch, allowing current to flow easily. Conversely, under reverse bias, when the polarity is reversed, it acts like an off switch, preventing current flow except for a tiny leakage current. Alright, and the PN junction can also be modeled as a capacitor. So, anal in this analogy, the depletion layer acts as a dielectric, okay, the insulating layer between the plates of a capacitor, while the p-type and n-type region acts like the plates. This capacitive behavior is important in high frequency applications. Alright, any doubt here? Anyone? So look at here. Hmm. Uh, there is a two figure, figure A for forward bias and for reverse bias. Okay, and we already talk about four. Any doubt here? So this is the IV characteristics. Okay, IV characteristics, current voltage characteristics. So it describes the relationship between electric current flowing through a component and the voltage applied across the terminals. So these are typically represented here. Look at here. So here uh, for look at here, IF milliampere and this microampere. So now we will discuss diode as a rectifier. So a junction diode is a semiconductor device that allows current to flow uh, only when it is forward biased. Okay, this means that if we apply an alternating voltage across a diode, the current will flow only during the part of AC cycle when the diode is forward biased. Okay, so during the other half of the cycle, the diode blocks the current. All right, and this unique property of diode is utilized to convert alternating voltages into direct voltages. Clear? And the circuit that performs this conversion, okay, is called a rectifier. All right, and the process itself is known as rectification. Clear, everyone? Okay, so now we will discuss diode as a rectifier. So there are two types of rectifier diode as a given below. Okay, half wave rectifier and full wave rectifier. So first, half wave rectifier. The half wave rectifier is the simplest type of rectifier, students. Okay, it allows only one half of the AC input cycle to pass through while blocking the other half. This means it only rectifies one half of each AC cycle. So look at here. So a half wave rectifier gives discontinuous and pulsating DC output. Okay. So mathematically, uh, if the input AC voltage is V V of t is equal to Vm sine omega t, and then output voltage V of t in half wave rectifier is what? So for output, it will be Vm sine omega t. For there is a condition for 0 less than equal to omega t and less than equal to pi. Okay, and for pi less than omega t less than equal to, we can say 2 pi. Okay, so look at here. There is a two circuits. So the circuit of a half wave rectifier typically consists of a transformer. Okay, and a diode and a load resistor RL. Okay, RL. This one is RL as shown in the given diagram. So the diode conducts only during the positive half cycle of the AC input, allowing current to pass and deliver voltage across RL. Okay, so the output voltage waveform. Look at here. The output voltage waveform here. This one is pulsating DC. Okay, it means it varies from 0 to a positive peak but never goes negative. However, the output is discontinuous because it is 0 during the negative half cycle, which is blocked by the diode. Alright, so let's see the characteristics of half wave rectifier. So the output voltage of a half wave rectifier in average or DC voltage of the rectified waveform. Uh, so since the rectifier only conducts during the positive half cycle of the input AC signal, the average output voltage VDC is equal to V peak divided by pi, where V peak is the peak value of the input AC voltage. Okay, this means the output voltage is roughly one third of the peak AC voltage, and the root mean square RMS. Okay, uh, voltage VRMS represent the effective a value of output voltage. For a half wave rectifier, it is Vrms is equal to V peak divided by 2. Okay, so this RMS value of important because it relates to the power delivered to the load. Okay, everyone. And if we talk about the ripple factor, so we can say the ripple factor R measures the amount of AC variation. Okay, present in DC output compared to the DC level, and it is defined as R equal to V ripple divided by VDC, which is equal to 1.21. So a ripple factor of 1.21 indicates a significant amount of AC ripple in the output, meaning the output is far from a pure DC signal. And if we talk about the efficiency, so we can say the efficiency eta of the half wave rectifier evaluates how effectively the input AC power is converted into useful DC power, and it is expressed as eta equal to PDC divided by PAC, which is equal to 0.4 0.06. Okay, this means only about 40.6% of the input AC power is converted into DC output power. This the we can say the rest is lost mainly as a heat or unused negative half cycles. And if we talk about the load current, so we can say the load current IDC is equal to VDC upon RL. Okay, this current is pulsating DC current that powers the load. Now we will discuss about the full wave rectifier. Okay, so basically a full wave rectifier is a type of rectifier that converts both the positive and negative halves of each AC input cycle into a unidirectional output. Okay, this means it rectifies the entire AC waveforms, unlike the half wave rectifier, okay, which only rectifies one half cycle. So here the circuit typically uses a central gap, okay, the central uh, gap. So we can say look at here. So the circuit typically uses a central cap transformer and two diodes, okay, to achieve this. So the transformer has a central tap that acts as a reference, splitting the input voltage into two halves. So during the positive half cycle, one diode conducts, and during the negative half cycle, the other diode conducts. Okay, so ensuring current flow through the load during both halves. Mathematically, we can say V input is equal to Vm sin omega t, and then output voltage mode of Vm sin omega t. Okay. So this means the output voltage is absolute value of the input sine wave, okay, resulting in impulse for both positive and negative cycles. So for positive and for negative cycles, look at here, this one. So the output waveform is continuous, unlike the half wave rectifier, because the load receives current during both half cycles of the AC input. However, the output is still pulsating DC as it varies between 0 and the peak value. So the waveform pulsating nature can be smoothed using filter circuits such as capacitors or inductors, which reduce the ripples and provide a more stable DC output. Since the full wave rectifier converts both the positive and negative half cycles of AC input, okay, into output. So it means it effectively utilizes the entire input signal. Okay. This means the output power delivered to the load is greater compared to a half wave rectifier, which only uses one half of the AC input cycle. Okay, therefore the efficiency of a full wave rectifier is higher than that of a half wave rectifier. Okay, now we will discuss about the ripple factor. Students, the ripple factor is an important parameter in rectifiers and is defined as the ratio of the RMS value of the AC component in the output to the DC component. Okay, it indicates how much AC variation is present in the DC output. So a lower ripple factor means smoother DC output. So these are key parameters of full wave rectifier. Okay, so the average output voltage VDC is equal to 2 times of V peak divided by pi. This means the average DC output voltage is proportional to the peak voltage of AC input. Alright, and RMS or we can say root mean square voltage VRMS, which represents the effective voltage, is VRMS is equal to V peak divided by V root. Okay, and the ripple factor is, the ripple factor is the ratio of the RMS value of the ripple voltage V ripple to the DC voltage. So it will be R equal to V ripple upon VDC is equal to 0.482. Okay, so 0.482 indicates there are still some AC fluctuations in the output. And if we talk about the efficiency, so the efficiency of the rectifier is the ratio of DC power output, okay, and to the AC input power. So this is expressed as eta equal to PDC divided by PAC, which is equal to 0.812. Students, this shows that the full wave rectifier converts a large portion of the input power into useful DC power. And the load current is the DC output voltage divided by the load resistance. So IDC is equal to VDC divided by RL. And the power delivered to the load is the product of the load current and the voltage, or we can say equivalently PDC equal to IDC into VDC is equal to V square DC upon RL. Now there are few diodes which are designed to serve some special purposes and applications. First, Zener diode. Students, basically mm, a Zener diode is a special type of PN junction diode that is heavily doped compared to a normal diode. Okay, this heavy doping results in a very thin depletion region. So due to these characteristics, the Zener diode can withstand high reverse current without getting damaged. This makes it robust and reliable when operating in conditions where normal diodes would fail due to high reverse voltage stress. So look at here, this one. Unlike regular diodes, a Zener diode is mainly used in a reverse bias mode. Okay, so when reverse voltage across the Zener diode reaches a particular value called the breakdown voltage or Zener diode VZ. So the diode allows current to flow in the reverse direction without getting destroyed. This controlled breakdown is the key feature of the Zener diode, and it is the primarily used in this breakdown voltage region to maintain a stable voltage. So this is the symbol of Zener diode P, this one. So one of the most important application of a Zener diode is a voltage regulator. Okay, so the circuit used for this purpose includes a series resistor, this one, okay, which drops across excess voltage from the input, and a Zener diode connected in parallel with the load resistance RL, this one, Zener diode, this one, and load resistance are both are parallel. And the role of Zener diode here is to maintain a constant voltage Vz across the load RL. Okay, so when even if the input voltage fluctuates. So when the input voltage increases, the Zener diode conducts more current to keep the voltage across RL constant. Conversely, if the input voltage drops, the diode conducts less. Okay, and this action stabilizes the voltage supplied to the load, protecting sensitive components from voltage variations. So in a Zener diode circuit, the series resistance R plays a crucial role by limiting the currents flowing through the diode, and this limitation prevents the current from exceeding the diode's maximum power rating, thus protecting the device from damage. And the Zener diode, a special type of diode designed to operate a particular region known as breakdown region, or sometimes called Zener region. Okay, so this region is reached when the diode is reverse biased, meaning the voltage is applied in the opposite direction to the normal forward direction of the diode. Unlike regular diodes that gets damaged if too much reverse voltage is applied. Okay, so the Zener diode is built to withstand this condition safely. And when it enters the breakdown region, the Zener diode maintains a nearly constant voltage across its terminals. Okay, which is known as Zener voltage and is denoted by Pz. This voltage remains almost unchanged even if there are variations in the load current or fluctuations in the input voltage. So because of this unique characteristics, the Zener diode is widely used as a voltage regulator to provide a stable reference voltage in electronic circuits, ensuring that sensitive components receive a constant voltage supply despite changes in the overall circuit conditions. So in a Zener diode, regulation circuit, the series resistance R plays a crucial role by limiting the current flowing through the diode, and this limitation is essential to protect the diode from the excessive current that could cause it to surpass its maximum power rating and become damaged. Okay, by controlling the current, the series resistor ensures the diode operates safely within its specified limits. So the voltage across load resistance RL denotes a VL remains approximately equal to Zener voltage Vz. Okay, and this ensures a stable and regulated output voltage. So look at here. So here the current flowing through the Zener diode called the Zener current IZ. Okay, IZ can be found by subtracting the load current IL from the total current I. Okay, so mathematically we can say IZ equal to I minus IL, which is equal to V in minus Vz divided by R minus Vz upon RL. Okay, So, to ensure proper voltage regulation, the general current IZ must be maintained between a minimum value IZ minimum, okay, and a maximum value IZ maximum. So, additionally, the power dissipated by the Zener diode given by the product of the Zener voltage and Zener current, okay. So, PZ equal to VZ into IZ. Must not exceed the diode's power rating to avoid any damage to the diode. Now we will discuss light emitting diode. Okay, so here an LED or light emitting diode is a special type of diode that is carefully engineered to emit light when an electric current passes through in it the forward direction. Okay, unlike regular diodes that simply allow current to flow in one direction, LEDs can actually produce light. Okay, so this unique property comes from the materials they are made of, such as gallium arsenide phosphide or gallium phosphide. So when the LEDs is forward biased, uh, meaning positive voltage is applied to the anode and negative terminal to cathode, electrons and holes will recombine in the semiconductor material. Okay, and this recombination releases energy in the form of light. The emitted light is nearly monochromatic, which means it has a very specific color or wavelength. However, if the LED is reverse biased, positive voltage applied to the cathode and negative to the anode, it behaves like a normal diode, okay, and does not emit light. It simply blocks current flow up to its breakdown voltage. Okay, so here uh, the color of the light emitted by an LED depends on the band gap, energy gap, Ag, of the semiconductor material used. Okay, so the band gap energy is the energy difference between the valence band and the conduction band of the semiconductor. So when electrons jump this gap and recombine with holes, the energy releases corresponds to the light's wavelength. This relationship is given by the formula Eg equal to hc by lambda. Okay, where h is the Planck's constant and c the speed of light. And the forward voltage drop Vf for an LED typically ranges from 1.8 volt red LEDs to 3.3 volt blue LEDs depending on the material and color. So light emitting diodes or LEDs are fascinating devices that produce light when an electric current flows through them. So the brightness or luminous intensity of an LED depends directly on the forward current, which we denote as IF. So as you increase the current, the LED shines brighter, okay, but only up to a certain limit. So if the current goes beyond this safe limit, it can damage the LEDs. Okay, so it's very important to respect the maximum forward current IF max specified by the manufacturer. So along with current, the power dissipated by the LED must also be within safe limit to avoid overheating and permanent failure. Okay, so one of the great advantages of LEDs is their fast response time. This means they can turn on and off very quickly, making them ideal for applications like optical communication, where signals are sent as light pulses and for indicator lights that need to react instantly. However, LEDs are sensitive to reverse voltage, unlike some other diodes. LEDs can only tolerate a small voltage applied in the reverse direction. And if the reverse voltage exceeds the LED's reverse voltage breakdown voltage, it can cause irreparable damage. Okay. And another key benefit of LEDs is their frequency. Frequency, yes or no? No. Efficiency. Okay. The another key benefit of LED is their efficiency compared to the traditional incandescent bulbs. So LEDs converts a much larger portion of electrical energy into light rather than heat. Okay, so this makes them more energy efficient and longer lasting. Okay, so look at here the IV characteristic LEDs. So the relationship between the forward current IF and the forward bias forward voltage drop VF across the LEDs is called IV characteristics. Okay, so uh, the curve here shows how the voltage changes as current flows through the LEDs and varies for different color of LEDs because each color corresponds to different semiconductor materials and energy gaps. Okay, so these characteristics helps engineers design circuits that use LEDs safely and effectively. Okay, so infrared there, infrared, red, amber, yellow, green, and blue. Okay, now we will discuss photodiode. So it is a special diode used in reverse bias, which conducts only when light is suitable wavelength is incident on junction diode. Okay, so the fundamental principle behind its operation is that the energy of the incident photons must be greater than the band gap Eg of the semiconductor material, which allows electron hole pairs to be generated. When reverse biased and illuminated, the photodiode produces a photocurrent proportional to the intensity of the incident light, making it highly effective for sensing light levels. Okay, and we know photodiodes respond very quickly to change in light's intensity, which makes them ideal for high speed optical communication system. So the photocurrent IPH uh, generated by the photodiode can be expressed mathematically as the product of photodiodes responsibility R in and incident optical power Pn. All right. So the total current flowing through the photodiode under illumination also depends on the dark saturation current ID, which is the leakage current present even in the absence of light. Students, photodiodes can operate in two modes depending on the application: photovoltaic mode and photoconductive mode. Alright, for better sensitivity, the dark current should be minimized. And common semiconductor materials used to make photodiodes include cadmium sulfide, selenium, zinc sulfide, and silicon, covering visible to near infrared light detection. Photodiodes find wide applications in light sensing, optical communication, medical devices, and barcode routers. Now we will discuss solar cell. So what is a solar cell? A solar cell is a special kind of p-n junction diode where one semiconductor layer is made extremely thin. This allows solar radiation to reach the diode junction without being absorbed by the upper layers. The solar cell converts solar energy directly into electrical energy through the photovoltaic effect without any intermediate steps. So, popular solar cells include nickel, cadmium, and lead sulfide. Okay, lead sulfide cells. among others. So the thinness of one semiconductor layer helps maximize absorption of sunlight right at the junction, minimizing energy loss. All right. So when sunlight hits the solar cell, it generates electron hole pairs in the depletion region of the PN junction. So these electron hole pairs are separated by the internal electric field at the junction, okay, which creates a voltage and drives an electric current. Solar cell uses the photovoltaic effect to convert light energy directly into electrical energy. So here the output current I from a solar cell depends on the intensity of the incoming light. So students, when sunlight hits the solar cell, photons transfer their energy to electrons in the semiconductor material, freeing them to move and create electric current. So the equation for the output current is I equal to IL minus ID. IL is the current generated by the light itself. This increase with more intense sunlight. Okay. So think of it as the useful current created by the solar cell when exposed to light. So ID is the dark current which flows through the diode even when there is a light. Okay, it is a usually very small but opposes the light generated current. So the net current I is the difference between these two currents. So when light intensity increases, IL increases, increasing the overall output current. Now, the open circuit voltage VOC is the maximum voltage a solar cell can produce when the circuit is open. Okay, meaning no current is flowing because the external load is disconnected. It represents the maximum potential difference between the terminals of the solar cell. For example, if you measure voltage across the solar cell terminals without connecting it to anything, you get VOC. Okay, so this voltage depends on the material properties and intensity of light. All right, clear? And the short circuit current ISC is the maximum current that flows when two terminals of the solar cells are directly connected together with zero resistance. And this current represents the maximum electrons flowing through the circuit generated by the incident light. In practical use, the solar cell is connected to a load, so the current is usually less than ISC, but this value helps characterize the cell's performance. Okay, so common materials for solar cells include silicon, nickel, cadmium, or we can say uh, here uh, lead sulfide and others, each with different spectral sensitivity and efficiencies. Solar cells are widely used in applications such as calculators, satellites, remote power systems, and solar plant panels for electricity generation. So let's see. Let's summarize our today's lecture in some brief points. So we already discussed energy bands in solids, then semiconductors, then superconductors, then types of extrinsic semiconductor, then semiconductor diode, then mobility of a charge carriers, then IV characteristics of semiconductor diode in forward and reverse bias, then diode as a rectifier, then special purpose diode, then Zener diode, then light emitting diode, photodiode, solar cell. Okay, so that's all for the today. Thank you for your attention. Now we will discuss some practice questions based on semiconductor electronics and logic gates. Okay, everyone. So ready for the practice questions? Yes or no? Okay. So please wait 2 minutes. Now students, we will solve some practice questions based on semiconductor electronics and logic gates. Alright, this is our disclaimer. Here we will solve some practice questions based on semiconductor electronics and logic gates. So our first question, the conductivity of a semiconductor increases with increase in temperature because, so the question is asking us to understand why the electrical conductivity of a semiconductor increases when its temperature rises. Specifically, we want us to identify the physical reason behind this increase by considering two factors: the number density of free charge carriers, okay, and the relaxation time. All right. So since conductivity depends on both these factors, the question is essential asking which of the factors change with temperature and how their changes affect the overall conductivity of the semiconductor. Okay. Given options: option A, number density of free current carriers increases. Option B, relaxation time increases. Option C, both number density of carriers and relaxation time increases. Option D, number density of current carriers increases, relaxation time decreases, but effect of decrease in relaxation time uh, in is much less than increase in the number of density. Alright, so which one is correct? Please solve this question, everyone. You have some time. Please find out the correct one. Okay, please solve. Which one is correct? Anyone? Please solve. So the correct option will be option D. Okay, let's see the solution. So as temperature rises, more electrons gain enough thermal energy to jump from the valence band to the conduction band in a semiconductor. Okay, so this process increases the number density n of free charge carriers, electrons and holes. Since conductivity depends on the ability of these carriers, an increase in n tends to increase the conductivity. Okay, so relaxation time tau is the average time a charge carries travels before colliding with something. So when temperature increases, the atoms in the crystal vibrate more intensely, causing more frequent collisions. This means tau decreases as temperature goes up, which tends to reduce conductivity. Okay, so the electrical conductivity sigma of a semiconductor is expressed as sigma equal to nq mu equal to nq e tau divided by m, where n is the number density of carriers, q is the charge of the carriers, Mu is the mobility, E is the electron charge, and tau is the relaxation time, and m is the effective mass of the charge carriers. All right. So even though the relaxation time tau decreases with temperature, which by itself would reduce conductivity, the increase in carrier's density and is much more significant. Therefore, the overall conductivity sigma increases with temperature in a semiconductor. All right. Next question. Carbon, silicon, and germanium atoms have 4 valence electrons each. Okay. Their valence and conduction bands are separated by energy band gaps, represented by AgC, Eg silicon, Eg germanium, respectively. Which one of the following relationship is true in their case? So, students, the question asks us to compare the energy band gaps Ag carbon, Ag silicon, and Ag germanium of carbon, silicon, and germanium respectively. These elements each have 4 valence electrons and their electrical properties depend on the size of these band gaps, which separate the valence and conduction bands. So the problem requires identifying the correct relationship among these band gaps from the given options. Okay. So to solve this, we must either recall the calculate the relative magnitudes. Okay, e.g. carbon, e.g. silicon, e.g. germanium based on their physical and electronic structure properties, and then choose the truly inequality or equality among them. So given options, option A, EgC carbon is greater than Eg silicon. Option B, Eg carbon is equal to Ag silicon. Option C, Eg carbon is less than Eg germanium. And option D, Eg carbon is less than Eg silicon. So which option is correct? Option A, option B, option C, or option D? Please solve this question and find out the correct option. Okay, please solve. Anyone? All right. Which one is correct? Yes, Ishika. Which one is correct? Varsha, Karthik, Shibam. Anyone? Please solve. Which one is correct? So the correct option will be option A. Okay. So let's see the solution. We know carbon, silicon, and germanium atoms each have 4 valence electrons. So this similarity in electronic structure is important because it affects their bonding and electrical properties. All right. So these elements have their valence band and conduction band separated by energy difference called what? Energy band gap. Okay. So and that they denoted as EgC for carbon, EgSi for silicon, and EgGe for germanium. These energy band gap of carbon in its diamond form is Eg carbon equal to 5.5 electron volt. This large band gap means carbon is an excellent insulator, and the energy band gap of silicon is much smaller. So Eg silicon is equal to 1.12 electron volt. This makes silicon is a good semiconductor widely used in electronics. And the energy band gap of germanium is even smaller, e.g. germanium is equal to 0.66 electron volt. Germanium also behaves as a semiconductor but with a narrower band gap than silicon. All right. So germanium also behaves as a semiconductor but with a narrow band gap, okay, than silicon. Comparing these values, we see that EGC is equal to 5.5 electron volt is greater than EG silicon 1.1 1.12 electron volt, okay. And similarly, carbon's band gap is also greater than of germanium. So it will be Eg carbon is equal to 5.5 electron volt. So we can say Eg carbon is equal to 5.5 electron volt is greater than Eg germanium is equal to 0.066 electron volt. Okay. Thus, the correct relationship among these options is this one. Okay. So we can say option A is correct. Next question. In N-type silicon, which of the following statement is true? Given options. Option A, electrons are majority carriers and trivalent atoms are dopants. Option B, electrons are Option B, electrons are minority carriers and pentavalent atoms are the dopants. Option C, holes are minority carriers and pentavalent atoms are the dopants. And option D, holes are majority carriers and trivalent atoms are the dopants. Okay, so which one is correct? C option is correct. Okay, so we know in the N-type silicon, the dopants are pentavalent atoms, which it means 5 valence electrons. Example, pentavalent dopants include phosphorus, arsenic, and antimony. So when pentavalent atoms are added to silicon, they donate extra electrons to the silicon crystal because they have one more valence electron than silicon's four. So these extra electrons become free charge carriers and increase the number of electrons available for conduction. Hence, N-type silicon electrons are the majority carriers, and holes are the minority carriers in N-type silicon. So trivalents, three valence electrons are dopants for p-type silicon, not n-type. All right. So thank you for your attention. That's all for the today. Thank you.